So we're going forward to the next sessions. And next session is the Toward Autonomous Comfortable Vehicles by Morales with the visiting associate professor from Nagoya University. So please, can you hear Luis-san?
Yes, I can hear.
Okay, if you are ready, you have you can probably start by.
Okay, I will present 20 minutes and leave 5 minutes for questions. If I am extending, please let me know. Hello, my name is Luis. I am visiting associate professor at University of Nagoya, and I'm going to talk about these comfortable vehicles. This is some research that I did in the past in ATR and Nagoya University. It's more of a tutorial than a real detailed technical talk. And I'm going to talk about comfortable vehicles from a roboticist point of view. And it's not only about automation, it's also about taking the consideration of the passenger and the comfort of the passenger and even of people around. Just going forward. Today's topics is research regarding personal mobility vehicles and ongoing and future research regarding something I have titled social mobility, but I'll be talking about this. In Nagoya, we have been doing research in autonomous vehicles. We have done research with autonomous cars, like this type of Prius type of car with the lidar on the top, and you try to do the navigation as safe as possible, but then there is also the comfort factor of the passengers and the other cars and people around. So I'm showing these videos because somehow we kind more or less of achieve level 4 of autonomous navigation, even in cars. But as a university, it's really hard to do experiments that involve comfort or discomfort of people. So that's why we had to develop a framework that we could run in the cars, but we could also use in our personal mobility vehicles because it's easier to do at the university level. Basically, we use the same software. We just and doing some personal. I don't call them wheelchairs. I like the term personal mobility vehicle because if you use the term wheelchair, everyone has a concept of assistance. But this can also be vehicles that are for personal use, and you can automate them, and they don't only need to be for people that need assistance. And the good thing of these personal mobility vehicles is that you can do experiments in the campus, in the buildings, and with people around. And even if you have an accident or you have an issue, they are not as dangerous as a car. If you have an accident in your car, it can be catastrophic. So that's very stressful. Also at university level, it's really hard to do these experiments, in my experience. Maybe someone has a good way to do them, but especially when you go out in the streets, you are not allowed to have bugs or issues like that. So some state of the art in autonomous navigation, some of the elemental technical elements is map building. Once you build a map, you can localize on the map. Once you localize on it, you can plan your paths, the local path planning and the global path planning, and you can achieve autonomous navigation. Of course, this is really hard. It's not that easy. That's why we still don't have autonomous cars everywhere. But this is more or less the typical components of an autonomous vehicle. So what is missing in these passenger vehicles, in difference to a normal robot, is somehow we more or less can achieve autonomous navigation. The navigation can be safe if you avoid obstacles and you can arrive to your goal without collision. But the question is, as in this workshop people have been talking about, how comfortable it is for the passenger. And safe and reliable are different from comfortable. So which is can be defined as the sense of ease or relief. This is just a conceptual figure of me trying to illustrate safe versus comfortable. You can consider we can have the horizontal axis as distance towards obstacles. On the left, very close. On the right, very far. Once you're more closer than very close is the collision region. So if you collide, your navigation already failed. Let's assume that on the vertical axis we have velocities. We have very low velocity on the bottom, very high velocity on the top. Once you go over vehicle specifications, it's very dangerous and your vehicle might just break down. So it's the unsafe state space. So you can consider that everything inside these blue regions is a safety space where you can navigate. And then the question here is, where do you want to go regarding obstacles and velocity so that the person on the wheelchair can feel safe and comfortable? So this is not that easy to achieve, and it depends maybe on everyone, and it has to be with subjective measurements, not only the objective ones. This is just an example of some work we did back in, this is 2013, when even in straight segments, when you're riding your autonomous vehicle, people have actually preferences. Let's say in these straight corridors, you can drive wherever you want, but if you are too close to the walls, people don't like it because it's uncomfortable. So you might assume you want to go in the middle, but we did experiments with participants, and many participants don't want to be in the middle, but they like the yellow areas. So the most comfortable areas for them were the yellow ones, then maybe somewhere in the middle, the red one and the blue one. And the reasoning for our participants for doing that is because if there is someone coming on the corridor on the other side, they don't need to avoid in these other people. So people like to be driving at 1/4 of the corridor. This is for a fully autonomous wheelchair, but you don't have control of it. So you're not controlling it. So people on the wheelchair are trying not to bother the pedestrians walking on their way. Our participants were Japanese, so we think that Japanese people like not to bother other people like pedestrians and other vehicles, so they want not to disturb other people. This happens a lot in Japan, like in the stairs, where people take one side of the stairs not to bother the people that want to walk fast. So we model this in a typical 2D map that we have, these occupancy grid maps, and if you model this type of cost function, you can add this to your map and do actually path planning in this kind of yellow areas, trying to avoid the blue ones very close to the obstacles and the red ones. So this is regarding where you want to drive in a straight corridor. Then the question is, how fast do you want to go? Not still the velocity, sorry. How about turning? Where do you want to turn when the vehicle is giving you a turn? So it happens that when you're being taken to, even if you have exactly the same geometric characteristics, there is a difference between blind corners and non-blind corners. So we understood that turning tightly in blind corners is very uncomfortable for people. So you have to start modeling blind versus not blind, not only the geometry of your map. So we proposed and designed some type of visibility analysis for the passenger, that where you have a non-blind corners, you can turn tight if there are no obstacles coming. And if there's a blind corner, probably you want to slow down a bit and maybe open a bit to try to avoid potential collisions with someone coming on the blind corner. This is just a small video showing how you could try to model these blind versus non-blind corners. This development was before ROS, so that's why we had some self-made OpenGL viewers, but so basically what we were doing here is trying to plan paths in the turns regarding its visibility. If it's a blind corner, you try to open it, to open a little bit to do the turn. If it's a non-blind corner, like this one, you can just drive tight if your obstacle avoidance or your human detector tells you there is no obstacle coming. So this is very simple talk and very simple conversation, but if you don't model this visibility of your robot, you might have uncomfortable effects for your passengers. Now we were wondering, okay, we can plan paths, so you can drive a certain speed. Now the question is, how fast should the robot run? And what is a human reasonable velocity? This is not that easy, actually, because we humans, we tend to get used to the velocities at which we are driving to. And at the beginning, we want to go maybe slow, but then as we drive, maybe slow is too slow, so we want to go faster. But how fast is fast enough? So we started doing experiments with the wheelchair. This is going really fast, close to 2 meters per second. So you can see this really tight turn, and she's not saying she was scared, but it was quite fast, you know. And if you go too fast and there are obstacles coming out, it's uncomfortable, especially if you have blind corners, so you have to be slowing down on all those areas. So you might say too fast might not be good. Safety should be a priority, so you want to go slow. So if you go slow, maybe you won't be crashing. You might argue that you will be achieving a safe navigation, but too slow, it starts being really uncomfortable and it's not a pleasant trip. So we're just doing experiments we had skin conductance sensors to see how much people start being anxious about it, and it starts being really uncomfortable. So it turns out that people they want to go maybe slow at the beginning, but as they get used to it, they want to go faster until a certain degree. By the way, we were doing experiments with questionnaires at the beginning, but then at some point I started wondering how much of the truth is being told by the questionnaires. So maybe the physiological sensing might be more accurate. And at some point we ended placing these EEG brain sensors on the brain of the passengers to measure the alpha waves. We measured heart rate and skin conductance. And we actually measured, I don't have the videos here, these velocity experiments in a self-driving mode and in autonomous driving mode. Why? I thought I had the videos of this one, but I don't have them. Anyway, so what we discovered in these things is at the beginning, even when it's self-driving, people like to go slow. And as they start getting used to it, they start going faster and faster and faster. And even though they go faster, after some point, they stop being stressed. So we call this effect habituation. It's like when you ride your car with your friend or your girlfriend that drives very bad, or your boyfriend, whatever. At the beginning, you're scared and not comfortable, but as you get used to it and you realize it won't crash, you become habituated to it and you stop being stressed. So what this means, I'm going to show these graphs. The graphs on the left is the first lap. The graphs on the right is the 9th lap. The two graphs on the top are the driving velocity. We can see on the left, the redder it is, or the darker it is, the slower, and the more yellowish is faster. So fast is 1.6 meters per second. So we see that in the first lap, they are going very slow, and in the 9th lap, they are going very fast. There is a lot of yellow, especially in the straight lines, because people started driving very fast. This was in a labyrinth we made in the laboratory. The second row is the heart rate. So we were measuring the heart rate of people. At the beginning, they are very nervous and the heart rate tends to be shorter, so your heart rate is beating faster. But as they get used to it and they're driving faster, the heart rate stops being that fast and people are relaxed, even though they are driving faster. And the same happened with the galvanic skin response, which is this sweat in your fingers. At the beginning, you're sweating a lot, but as you get used to it, it becomes lesser and lesser, even though you're driving faster. So what this means is that when you model velocity and try to model velocity based on physiological sensing of people, you have to consider these degrees of habituation. Also, when you do experiments, the first time people experience your robot or your system, they might be excited or stressed because it's the first time they have it. So you have to give them time to get used to your system so you can actually measure the real response of a person being used to your system. Because if not, they will be stressed just because it's the first time they do it. This is what this experiment shows. And regarding habituation, in velocity, this is for self-driving and and autonomous driving, people at the beginning likes to be slow, which would be when they are beginning, they like to be slow. As they get more experience, which is the horizontal axis, they go faster and faster until there is a saturation level or comfort level. And maybe this comfort level is different within people, but you have to model this habituation experiment when you do experiments with your robots. You start slow and slowly start speeding up, speeding up, speeding up until you think, or the physiological sensing data could tell you they got used to it, and you just can let them go faster and faster because they are already habituated. So even in a normal self-driving car, I think at the beginning it's okay to go slow, but as people get used to your car, it's okay to go faster and faster if you will have your objective safety mechanisms in your car on, like obstacle detection and avoidance. Yeah. So the whole point of these slides is that in this human-robot interaction, because I consider that a human driving a personal mobility vehicle are having an interaction with the robot. So the people acceptance is key. And the robot has to be safe and comfortable. And it has to be safe and comfortable for the pedestrians, for the other drivers, and for the passengers. So there is a three element system here. And I also think that it might be worth doing a lot of research in bioinformatics and do measurements of the state of the passengers. And one thing I think at some point we will end doing, or we should try to be doing, is to give real-time feedback to the autonomous control loop. I have never done this in real time, but I think this is something that we will end doing at some point. You will have your feed-forward navigation model. You send it to your controller. You have your autonomous vehicle running, which might be safe and maybe comfortable. But once you give the feedback of the human state, you can regulate it to go faster or slower or things like that. And you could use the alpha wave of the brain or the heart rate or skin conductance, or I don't know if the smartwatches will be a good mechanism to help us to do this. Just to extend a little bit, I have a couple of minutes more. The navigation and the interaction is between the passenger and the autonomous vehicle. And the passenger can give the goal to the autonomous vehicle, and the robot will take you to your objective. And this is more or less what we all do. However, what happens when there is pedestrians around or other people? This is maybe what people are trying to also solve with VR. But at some point, I think it's important to be able to give some navigational cues to pedestrians around. So if there is a person in the wheelchair, somehow you have to give a navigational cue of how you want to navigate so these people take action and avoid you. So one way to do that, we were thinking, was to do some light projection. When you face pedestrians and they are coming towards you, usually we don't have visual cues or any cues, so that people will not know how we are trying to avoid them. If you use some type of light projection, maybe you can show the passenger and the pedestrians around. And we also place a winker just to do the comparison and see which one seemed to be better. And we implemented this in a wheelchair. And this is the total no motion cue, which is usually what we all do in our wheelchairs, but it's really hard for the pedestrian to understand how the wheelchair will avoid. Once you have light, maybe you can show how you're going to avoid, and the person walking can understand this and avoid you. And you can have the winker, but the winker is not that useful for, especially for the person sitting down, because he won't understand how he will move. And we have the handheld display as well. But the handheld display is only useful for the passenger. So we understood that giving some type of navigational cue to the passenger and pedestrians around is very useful. We did it with light, but of course we know and we understand that this is not very useful for outdoors. I don't know how we can do that. Maybe some type of laser kind of thing. But well, this was just some basic research and that we were trying to do here. And just to finalize, I just want to give some type of the interactions we have. When we have a single vehicle, you want to achieve autonomous navigation for the passenger. When you have pedestrians, it's not only the passenger and the vehicle. You have to consider all the people around, and there is a whole system that creates a comfort system between these two elements. And in most of cases, when you're driving in a personal mobility vehicle, you don't want to go alone. You want to go with a friend or someone to talk. So you have to model some type of side-by-side motion with the pedestrian. So you have to be able to do this shared planning, which is actually really hard, as we humans do actually, because we want to talk with someone. And then the system starts being more complicated when you're moving in a group and you have to avoid other people and groups of people. So I think there are a lot of open issues, like understanding other people's intentions and how can you give motion cue to everyone in the system. So I ran out of time, so I will stop here.
Okay, thank you very much for listening. So now we move to the question and answer question. So if you have any questions, please raise your hands. Okay.
Hi, I'm Bashak from University of Oulu. I was wondering about the part when you talked about taking into account the physiological responses in a feedback loop. So I was wondering, because I would expect the human physiological response to be kind of slower as opposed to a normal feedback that we use in a control loop. So do you have any, I don't know, ideas about how to, or like, can you speculate if there are any, if you expect any issues to appear, or like how to avoid those?
Well, you will always have a delay. That there's nothing you can do about that, I think. But at some point, you have to take into consideration the feedback of the person sitting down, or somehow with a joystick or the physiological sensing. If it's a joystick, you can do it, but you have always to be pressing the joystick. So we thought that heart rate was a very good way to measure this, you know. It doesn't need to be in real time, maybe. You just can have a model of yourself, because everyone is different and everyone's heart rate is different. So I think will end happening, like when you have your watches, when you jog or run, you have a model of yourself and you can say how higher you are of your normal state. And based on that, once you connect your watch to your car or the personal mobility vehicle, you will be able to say if you're enjoying the trip or not. No? Of course, you need to have context, because if you're late to your date and the system detects you are stressed and goes very slow, you will just get more stressed because you're running late. No? So you need some context with your calendar and all these kind of things, which makes the thing harder and harder. But somehow you will need to connect the human state to the robot, in my mind, you know? Yeah.
Okay, thank you.
Okay, thank you. Have any short questions? We have one more question, Kendall.
Yeah, so I'm sorry. I think it was an excellent talk. I'm sorry that I couldn't make it to the beginning. My question is, when your models or your wheelchair robots navigate around, do they use any visual information like optic flow based, vector field based visual information from cameras?
No, we were not using computer vision. We had a very good robot with very good encoders and very good localization based on LiDAR. And all the modeling we did was doing raycasting with LiDAR in the 3D map of the environment.
Yeah, so the reason I asked is because I totally agree with the questioner and what you said, that it would be really nice to have a physiological feedback, but you have to do that like within the scope of safety. And if you have something like a velocity vector field analysis always ongoing, then I think you can approach that safe zone that okay, no collision is going to happen, but still you have that range in which people's experience or physiology can have an effect on that. I really like that. Actually, my talk, I'm going to kind of go exactly the same direction with cars. I was really fascinated by a talk.
Okay, can I just add one quick thing? At the beginning, we were only doing questionnaires, but we were doing experiments with the wheelchair going really fast, very close to the obstacles. And we thought that was quite scary, but some people, we had some American football players testing the wheelchair and they were never scared, no? So in the questionnaire, they are saying, no, I'm not scared, I'm not scared, I'm not scared. So we start wondering how true that could have been, actually. So when you actually measure the skin conductance for the heart rate, it tells a lot about that. But then you start wondering, it's a philosophical question, who is telling the truth? Your physiological response, or once you pass it through your conscious thought and you reply the questionnaire and you say, I'm not scared because I was trained not to be scared. I don't know, as you said, it's a very interesting thing there. I think both are important, and if both results have the same response, that's the best case scenario. And in most cases, I think it is. Yeah. By the way, I forgot to mention that some of this work I did with Sawabe, who is organizer of this workshop, because he was also doing a lot of physiological sensing in his PhD. And Professor Kambara. Yeah.
Yep. So thank you very much for asking questions and nice discussions. Okay, now we would like to move to the next presenter, which is the Zulos Platinius-san. Now we just ask the questions, right?
Okay.
So we have 20 minutes presentations. We have like 5 minutes question and answer. So can you get ready for that?
Yes. Okay, so I think I need to find a way. Okay, so I think the best way is to start the presentation and then try to share it, right?
Yes, please share the slide information
Yeah,
so we can see.
Okay, how do I do that? Okay, let me share screen and this is being shared. And then
Yeah, that's very nice. And open up with the full screen. So he's from the University of Szeged. Sorry, it's hard to pronounce. So when you are ready,
it's Szeged from Hungary. Yeah, I'm from Hungary, and it's the University of Szeged. And as you see, we have a lot of people involved in this project. So, but first of all, thank you very much for the invitation. I'm really eager, and I'm really kind of flattered by you approaching me. So this story is basically started like 2 years ago when we have an economy department, and the economy department was mostly interested in technology acceptance. So they had this program of various parts of technology, how they are going to be accepted and approached, and then they came to us to the psychology department, and they say, hey, can we do something together? Like we always use these questionnaires, but we would be interested if we can do something like a physiological measurements or something like that. And then so basically the story is that that's how every time somebody comes up with a new piece of technology, then there's always a question, will it's going to be accepted? And if you look at the history of technology, then you can see that some of these technologies stay with us, and some others are kind of people try it, but they don't use it. So it's really interesting. If people start investing in self-driving technology, then obviously that's a big investment, and they are interested in how it's going to fly and why. And obviously we have the biggest research limitation here is that we are already, like, when I say we, I mean like humanity, we are already in the phase of investing a lot in this. And we did actually very little in terms of like in-depth situation-based analysis on how people will react to that. And by that, I mean people actually traveling on board of these vehicles. So when we look at that, you know, when we ask people about their opinions, they might not be exactly the same opinions when they just think about it without actual experience and having actual experience on board of these vehicles. People have expectations and people have attitudes, and that we can measure. But when they have onboard reactions, that could be something different. So our question was, is that are these, because, you know, people in economy, they have really elaborated a lot on models of acceptance. So they have very sophisticated and hierarchies of technology acceptance, and they have a lot of literature on the suitability of these models. But when it comes to something like autonomy in technology, even if it's just autonomy, not really autonomous, but that's really something new, which these traditional measures may or may not be suitable. So, and if you look at like the high-tech measurements some years ago, people started obviously worrying about questionnaires, but that's what they still mainly use. And then when they wanted to give something like experience, then they started using video presentations and 3D stimulations, and then they do some EEG measurements, like you see in the picture on the left side, and also some kind of you know, simulations and eye tracking, so, but obviously this is not like related to the physics of a real car, like a real journey. So, again, the question is that when you take someone and let them sit in a real self-driving vehicle, can you get something more information, and can you get useful information that will be useful also for assessing technology acceptance and also for the development of these vehicles, so that they are going to be like more fit the need of the humans that are going to use it. And in that sense, it was for us like a really so I'm sorry for the Hungarian title. I'm just trying to say that when you start doing something like this, then it's really easy to get into the magazines, like the National Geographic, you know, came after us and they said, oh, you're doing you know, some craziness with the EEG and eye tracking and all these measurements. So the reason why it was really exciting, because it almost it was the same time, you know, we in psychology, we used a lot of these measurements, but always it was tied to the lab. So both like eye tracking and EEG, you know, you needed to stay in the lab. And now, just a couple of years ago, actually, we started using new pieces of technology that allow you to get outside in the world and do all kinds of measurements with relatively in a relatively comfortable way, where actually somebody can just sit in a car and then you still have all these measurements available. And So that was like a coincidence of we got these requests, and then we were already playing with these mobile devices. So we started our work together, and then a typical experiment that we do, like what you see on this map, is where we started this work. We didn't have like access to like dedicated fields. But we have this small local airport that has a runway, and in that sense, it's a safe because as you see on the map, even if the car runs, off the track, it's just going to be on the open field. So that's how we got like ethical approval for these runs, and then the idea is that we take a car that has some kind of self-driving capabilities. The first car that we used was like a modified Tesla that, some of these, there are few countries that actually you can allow these Teslas for the full extent. But when you go to these fields that are safe, that you can open up these extra possibilities. So basically, it was like a modified Tesla that can actually follow this track that has few turns, and then it can actually navigate through these through the runway and the service road to the runway. And then the design of these experiments is that obviously we still ask people about their opinions before and after, but then they got all these measurements and they sit in the car, and then they go a couple of turns in self-driving mode, like autonomous AV mode, and also a couple of turns in human driver mode. And then obviously the order in which they experience these things are being randomized. And then we measure not everything all the time. We started only with the EEG and eye tracking, but then we started putting in accelerometers on. We have this. I'm not sure if it's on me right now, but yeah, we have these smartwatches that are being it's under development, so it has this ugly case, but it has very powerful sensors. It has it measures accelerometers that are like 200 hertz accelerometers in there, and also it obviously measures heart rate and blood oxygen density. And then we also used GSR sensors that are, easy to put on and easy to wear. And basically from the get-go, our goals was to find those kinds of dimensions in sensitivity that includes differences and correlations in personality, psychology, but most importantly, obviously, in between these two states. And then, so that was the first, 2 summers that we did these kinds of measurements, and then we went. So it was in a sense it was easy to get people's opinion on. Or get people's, reacted. But basically what we had when we wrote this article is that it's easy to measure in EEG and eye tracking. It's easy to measure differences between the autonomous mode and the human-driven mode. And it suggests an overall preference for human drivers. And so it comes out from various measurements, like from EEG, you can discern measures of that kind of arousal that is like a mostly unpleasant arousal, and also from the eye tracking, you can clearly see that people are more alert and not necessarily in a positive way when the car is driving itself. And we have a number of relations between psychological states, even personality dimensions, and then and in between the values that we measure. So what we think is useful is that if you are developing these vehicles, then we can help people, and actually that's what we do right now, that we can help engineers to find those parameters that actually go into these physiological responses, and perhaps we can diminish the difference between autonomous driving and in between human driving, or if we are really lucky and if we are really skillful, in the future you may even reverse the preference, or you can identify main components of discomfort and try to handle them, and also you can find individual differences, and so that you can kind of get a feel for how can you tune the vehicle to that particular person. And that is what I think starts growing from our research as a more interesting way of looking at things, and it really has a strong connection to the talk that we just listened before my talk, is that when you can identify these parameters of an experience between technology and human, and you can start continuously monitoring these, then you are in a position to make real-time adjustments of these parameters of experience. And it needs to be stressed that obviously you can only do that within the range of safety. But we believe that because we're different, and machines start to be faster and more reactive. So we believe that there's a range in between. We are still within the range of safety, but you can start making changes into these parameters of experience, so that the user experience can be continuously adjusted to the person. And so that is kind of breaking with these old tradition, is that when you design a car or when you design any kind of transportation, then you have to go for like a universal design that is going to be the best for everybody. You can actually have it in mind that you're going to have some kind of leeway or some kind of range in which you can adjust the parameters of running and turning and braking and taking over. You can adjust these parameters, even maybe including like lighting inside the car, but you can adjust that to the need of the people who are actually riding or traveling in that car or in that vehicle. And then that includes, it's not only personality, but also like actual mental processes. Sometimes, the same people, they want like a pleasant journey with, slower and enough room to observe their circumstances. And other times they wish to hurry it more, or wish their preferences for this, even for the same person, the preferences can change. And obviously, this includes not only transportation. It's like once you have these, a way to identify user experience through these measurements, then you can start designing softwares or other tools that that are sensitive to these things. And so part of these projects that we do with these smart devices, part of these projects is to identify immersion and flow, like a psychological flow state, and try to see again in a personal way that how that particular person is going to get into this involved, immersed state. And it doesn't have to be again driving; it could be anything. And one of the companies that we collaborate with, they are really interested in how can you expand your own, in order to raise the standards of living, how can you kind of guide yourself with the help of these smart devices, to guide yourself to experience being immersed and being in flow ever more often. And then obviously we have to learn a lot about these things, but you can kind of see that how it goes together with the work on the self-driving cars. If that is something in the future that people are going to see themselves like being in this immersed and meaningful states, then obviously they're going to like them more. And then I kind of think I didn't really check what was the time when I started, but I kind of feel like it's getting to the end. So let me wrap this up. When you look around on the market, you already see that people are like deep in these kind of questions. So we just learned like a week ago that Harman and Samsung are working on these continuous eye tracking for assessing stress levels and fatigue. So, and I believe that even in Bosch and in BMW, they are working on similar systems to assess fatigue and stress. But as it goes to the research development ambitions, I think our ambitions point a little more beyond this, and to see, how can you not only, based on fatigue and stress, but how can you kind of assess experience in that is useful for both a developer or somebody who wants to see the future of us, working together with semi-autonomous technology. So here's our team. This is a part of the team that's always on the field, and it's these people are, partly from the economy department of the University of Szeged, and from the psychology department, and also some people who are experts in using these mobile sensor technologies. So again, I thank you very much for the invitation, and I think I'm ready for questions.
Okay, thank you very much. So now is the time to the question and answer. If you have any questions, please raise your hands. Okay, I got one question actually. So it was a very interesting talk. Thank you very much. I'm Taishi Sawabe. And my question is that when you done the experiment, have you also considered about the passengers' driving experiences? Does it affect any kind of psychological measurement as well?
Yeah, so obviously when we start these measurements, we do like a big assessment, a psychological assessment, and also their experience with how long they hold a driving license and how, and then we had these we also had these feelings that people who are longer, and they might feel like a more detached from this, basically because they know how to drive, and if the car is doing something different, then they are going to be like more in a distressed state or something. But I have to report you that so far, driving experience doesn't seem to be like a major point in these things. And also what Louis, I'm sorry that I use your first name. That's all that I see on the. But Louis was saying that it's always a question what you say or what you think you're going to feel and how you're going to feel. We also kind of see that some people who feel like they are really embracing this new technology and are really fascinated. Some of these people are actually more stressed than the ones who report that they are uncomfortable with the idea. But I'm just saying that none of these is like how much I feel like I'm accepting these and how much experience I have. None of these seem to be like a major factor in their physiological data.
Okay, one more question.
Hi, my name is Jayant. I'm a researcher at Waymo. Thank you for the talk. I thought it was super interesting. I have a couple of questions. The first one is, do you have any insights on what were possibly the main causes of discomfort for people when they were in these autonomous vehicles? Was it the turns or the acceleration or just the psychological effect? And the second related question is, do you have any measurements or experiments to see if there were noticeable driving differences between the human driver and the autonomous driving?
Yeah.
Thank you.
So when we submitted the article, then one of our reviewers were really excited about these, and that was exactly the reason why we included the accelerometers in the second phase of measurement. So what we did like a couple of months ago, we recorded tons of data on these runs, and also we started using unforeseen obstacles when the car has to do like a really quick turn, a really quick modification, and then so if you ask me, I think I cannot say this for sure, but I think that the difference between the actual driving situation of the physics of the mechanics of the car, how it's moving, I believe that what's actually go into these distress or into these differences, and that's also kind of the idea that I say it makes sense to measure these people, because now you go to the engineers and they say, let's do some measurements on how like very good drivers drive, and try to modify the drivetrain or try to modify the dynamics of a autonomous vehicle, and then we do a measurement again, and then we say if that difference start diminishing, and then I think that's a really important point. So thank you very much for that question. And your other question was, I'm sorry.
Yeah. So the other question was if you had any. So I guess if you had any intuition on what was really causing the discomfort, or what the takeaways might be for just designing better driving behavior from these self-driving cars.
Yeah, so I think that if it really, I mean, we have to test it, but the reason that we included these acceleration-based measurements is that now actually we are in that. So the analysis is not done yet, but now we in the phase of really saying something that okay, looking at all these data, there's a very clear difference in acceleration and deceleration and takes and changes. And if that is the case, then it's almost, you can almost conclude that yes, it's because of the difference in how the car drives itself.
Thank you.
Chris-san, can you hear the last question? Hey.
Yeah, sorry, just 3 quick questions. maybe I miss it, but I want to ask you, how do you use this gazing device you had? Because I think the gazing of the passengers sometimes tell a lot about their state. And what did you find to be the most useful or most accurate or honest physiological sensor or sensing modality? Or is a combination of all of them? Or what are your thoughts about those sensing
Well,
devices?
so I think it's the major difference is, I believe, it's not necessarily the device, but the analysis.
Mhm.
So there are, to my mind, there are two kinds of analysis, and one is like, even if you think about the EEG or the eye tracker, is the one of the ideas is that you have to find the optimal uh, frequency in which you have. So one way of looking at these data is that there's a lot of noise, and there's one or two frequencies, or in the eye trackings, there's one way of looking at the saccades or looking at the fixations, or so one way of looking at these complex, because these are complex data, is that you think it's a lot of noise, and there's something in the noise you have to kind of filter out, and then you're going to have some. And I think this is an old way of thinking. And a new way of thinking is that as long as the noise is not coming from your machine, as long as the noise is coming from human behavior, then you have to look at that as a complex data and do spectral analysis on that. So basically what we do, we have these unorthodox ways of looking at all the data that we have. We always do multifractal analysis that allows all these different levels of changes, all these different interactions that are going on in the data to speak up. So we are not looking for like this golden ratio or like a golden frequency band. We are looking at the entire data set and do fractal analysis on that and see how, say, measures just like the width of the multifractal spectrum, how that changes. And if it changes in abrupt ways, that always goes together with a change in people's mind. So to answer your question, basically how we use all these all these measures like traditional ways too, but we always put together these nonlinear and complexity measures, and I think that's where most of the time we find meaning.
Okay. So how do you use the eye tracker? You were measuring where people are looking at outside the car?
So we basically, we are not really measuring of how what people are looking at. We're just measuring, the displacements of their pupil. That's
Okay,
that's our
blinking to detect
displacement of a
stress.
pupil. It provides like a big like a fluctuation data, and we use that fluctuation data to see how people's contentment or how basically we just see if there's a change because there was a dangerous situation, then it comes out easier. To be honest, with these variable, this one is pupil labs, with these variable eyeglasses, really making a very exact or a very punctual measurement on where people were looking, it's kind of iffy. So still, I think with the monitor mounted eye tracker, you can still be more or less sure where people were looking. When you start going out there in the real world, it's kind of it's not really that punctual, or not really that reliable. And that's why we most of the time we just base on pupil displacement. That's our basic data.
Thank you.
Okay, so thank you very much for joining and answer questions. Thank you for both of them. So this is the end of the section. Thank you very much.
so it's time to the start time to the next session. But so we have to prepare the presentation of the invite talk. Please have a short break. Please take just taking a coffee.
Okay.
Cyril?
I'm sorry. So the situation is that like in a half an hour I have to go to teach. So I'm not going to be able to attend to the next. But I really I was excited to be here, and I really thank you very much for the invitation again.
So thank you, that I'm Kambara. So thank you for your presentation. We had this very good discussion about your talk. Thank you. So
Thank
the
you.
next the presentation. So Cyril, this are you here? Okay. Please try to share your screen.
Yes. Thank you. Thank you.
Thank you for joining us today. So okay.
Well, thank you for having me, and good afternoon, everyone.
Yeah. Okay, I can see your screen. Okay. Please wait a few minutes.
Yeah, no problem. No problem. That's fine.
Hey, this is Sawabe from the Nara Institute of Science and Technology. I'm an assistant professor. Good to see you, Cyril. How to pronounce your name, though?
Yeah, Cyril Deals.
Okay, Cyril Deals. Good to see you. So
Yeah.
last session was very interesting. So everybody was like discussing a lot. So that's why it's a bit late, delay for. But
Yeah.
I'm sure the people will come back in here in a minute.
Yeah, I was looking at the sessions. It's a shame I couldn't join it, but if there is a way to share the presentations afterwards, that would be fantastic.
Yeah, and I'm really interested about your work. Actually, I was looking for because you guys, in my perspective, you guys are more like from the design thinking styles, right? No more like engineering styles, right?
Yeah, I mean, I've been working with a lot of car companies in the engineering side of things, but my particular interest is what it means for design, really, in terms of future vehicle design, but also how we design the interactions within the vehicle. Yeah.
Yeah, that's I'm really looking forward to see your presentations maybe in a few minutes. Yeah. So please wait for a moment, yeah.
Yeah, no problem.
Okay, let's start this last session. So last session is the invite talk session. So speaker is Cyril Deals from Royal College of Art, Toronto. Thank you today for your today's presentation. So please start when you're ready. Okay, I can see. We can see the slide.
Yeah.
Okay, please start.
Great. Okay. Well, first of all, thanks everyone for the invitation to give a talk at your workshop. I look forward to see the other presentations when I get a chance. It looked really interesting. So it's a shame I missed them, but hopefully it's an opportunity. So what I want to talk about today is designing for motion confident in automated vehicles. And particularly looking at sort of mitigation strategies that we've been working on over the last few years. And also end up with a short discussion around common protocols in which we hopefully can work together, all of us across the globe, to resolve some of these issues and work on motion sickness together. Just to start, perhaps I'd like to start with this image of Rinspeed, which is now quite an old image, but actually I think this was one of the images that really set me, really started off the discussion around motion sickness for me, because obviously when we're looking at this, if anyone with a bit of motion sickness knowledge would clearly understand that this might create some problems. And I think here you can also see the power of design in that by actually making it a reality in terms of a concept, suddenly becomes very clear what are the challenges and the issues that we need to think about for the future. And for a very long time, I think the issue of motion sickness wasn't really acknowledged as such. And in fact, I even wrote a paper about it, calling it the elephant in the room. But I think since a lot has happened, is also evidenced by this workshop today, which looking at augmented reality and virtual reality in automated vehicles and comfort. So it's now widely recognized as a topic that's worth exploring. And again, as indicated here by Peter Schreier, who's the president of design at Hyundai Motor Group, whoever solves the motion sickness problem first will have a real competitive advantage. So it's really seen as a really key aspect in the future of mobility. And if we look, for example, at the number of publications referring to, in this case, motion sickness in virtual environments, we see a massive increase in interest within the topic. And likewise, if you look at motion sickness in vehicles, car sickness, that there's also a big increase in interest within this space and lots of more publications over the last few years. I do want to say a little bit about what I call automation intoxication. So everyone's talking about automation, and it is very exciting and it's got a lot of potential. But we also have to remember that a lot of the questions related to motion sickness in future vehicles and automated vehicles actually also holds true for shared mobility. And shared mobility we see as one of the most solutions that are got most potential to actually really increase the sustainability of our future transport systems. So I think it's really important that we don't forget about shared mobility as another area where we really need to think about motion sickness. Now, to very briefly come back to what we mean by motion sickness, I know that everyone here in the workshop knows about motion sickness and understands that it's being caused by a wide variety of environments. And of course, that it's a natural response to an unnatural environment. It's not a sickness as such, it's just a normal response. And when we think about car sickness, then there's essentially two ways to really think about it. The primary cause of car sickness, of course, is exposure to actual motion. And so when we think about managing motion sickness in AVs, then we can think about what's the chosen route, how do we plan the path, what are the vehicle maneuvers, and how do we perform the vehicle maneuvers, and also what sort of driving style do we want to use in AVs. So that's all very much based around the basic motion pattern that the vehicle is taking. But in addition to that, of course, there's lots of modulating factors, we refer to it, that have an impact on the level of sickness by its mechanism between expected and sensed motion. So when we think about motion sickness in these future vehicles, we need to think about the design of the vehicle interior. So for example, the size and locations of windows, the orientation of the passengers inside the vehicle, but also the design of the in-vehicle activities. How do we design these interactions where people are reading or watching or socializing? It's very important to keep that in mind. And last but not least, we also can provide certain motion cues to compensate for some of these lack of cues that we receive, depending on the type of design that we're having. So they are sort of two major categories of interventions and design strategies when we talk about motion sickness. But before that, I'd like to just briefly also mention a fairly recent study that we've done looking at the causes of motion sickness. And this is quite interesting because it's a very large-scale survey, this, about thousands of people across the globe, so in different parts, Brazil, UK, US, Germany, China. So it gives quite a good indication. And of course, if you think about the causations of car sickness, there's many terms of being referred to: curvy roads, reading, using a device, writing, watching a video, stop and go traffic, all these sort of things that are related to the vehicle dynamics and the in-vehicle activities. Also, what we can see is that motion sickness particularly happens in passengers in the back of the car, less so in the front of the car, and very rarely in actual drivers, although it does happen. Likewise, if we compare the level of car sickness reported across the different countries, so you can see here Germany, UK, US, Brazil, and China, you can see that overall there's a big impact of culture or ethnicity. We don't quite know what it is. We probably think it's about related to ethnicity and a genetic background. But what we can see is that the Chinese are particularly susceptible to motion sickness. And what's more, we can consistently find that females are more susceptible than males, and also that susceptibility actually decreases over time. So the older we get, the less susceptible we get when it comes to car sickness. So that's a bit of background to what I wanted to talk about today, and I really want to talk about mitigation strategies that we've been looking into, but also point out to one particular study where we look at the evaluation of a more complex mitigation strategy, which possibly has got quite interesting implications for future research methods. And finally, I want to say a little bit about common protocols, particularly related to the international standard that's currently out there. So starting out with mitigation, I think we all know the different concepts around the world that we've seen for AVs. They all look superficially very different, but actually in essence, they're very similar. And one of the key factors that keeps coming back is the idea of facing seat arrangements. So the idea is that we can use AVs to actually facilitate social interaction by rotating the seats. And of course, almost every company has been looking into this and providing some initial concepts. But again, from a motion sickness perspective, we of course know that that's probably not the best way to go, particularly when we think about those who are particularly susceptible to motion sickness. And what you can see here is a study that we've done a few years ago with Jaguar Land Rover, where we created a van that we kitted out with different seat, and we had different seat arrangements, so the long and the shorter distance between people, slight inclination, slight rotation of the seats inside the vehicle, and of course the mere fact of traveling forwards or traveling backwards. So during this trial, people were asked to perform regular office tasks. And there was urban driving was found to be more provocative than motorway driving, as we probably already know. But what we also found is that rearwards travel increases motion sickness by a factor of 5. So that's quite significant. And all those participants reporting high levels of motion sickness was in the rearward facing position. So there's some clear indication that rearward facing traveling induces more motion sickness. And I suppose what this means is, first of all, that we need to be careful about, do we really want to do this? So designers need to think, well, in what cases do we really need or want rearward-facing seating arrangements? But there's also questions around, if we do want to create these environments, how can we perhaps augment the environment to actually compensate for the lack of outside view and also the ability to anticipate future motion? And so this is quite an interesting element, and I think probably in some of the presentations that I've seen, the abstracts of this morning, are already referring to this anticipation as a mechanism. And one of the key questions still is what is the relative effectiveness of different sensory modalities, but also how does it actually interfere with what people are doing inside a vehicle? So something might be very effective, efficient, but actually, what's the acceptance and what's the experience inside the vehicle? I think that's really important. And finally, when we think about alternative seating arrangements, we also need to think about perhaps innovative seating approaches that can actually help people to manage motion sickness themselves. And again, self-management is something that's not particularly well explored, but I think it's got a huge potential as an area of research. So I'd like to start now with the next section where I'd like to talk about anticipation. And one of the key publications in this space is, of course, Rolnick and Lubov in 1991. And it's also one of my favorite diagrams of motion sickness research, where you can see yoked participants being spun around a vertical axis device, where one person was in control of the head movements they made, and the other person was just passively following the head movements. And of course, the person who was actually actively involved in making the head movements reported less motion sickness than the passive participants. So this mechanism has been known for quite a long time. And so the question is, how can we extrapolate this, or can we extrapolate this to a situation of automated vehicles where people are no longer in control of the vehicle, but we perhaps can still provide cues that actually reduce the level of motion sickness? And this is one of the earliest studies that we've done. This is a study that we've done together with BMW. And we had a 80-minute urban drive, which you can see here on the test track. And it included various corners, roundabouts, right turns, left turns, accelerations, decelerations. So quite a provocative environment, but not dissimilar to a normal city drive. And so we've instrumented the participant who sat in the front of the vehicle with various measurements. And we also asked the participant to actually perform a visual search task, in this case, the SERT task, surrogate reference task, where they had to find targets amongst the various distractors. And they had to do this continuously using a little controller held in their hands. And I'll show you a little video here. So what we've done, we had one condition in which there was no cues provided whatsoever. And in another condition, there were auditory cues provided that indicated what maneuver was coming next. So you can hear that here.
Right hand corner ahead.
So here you can see that you can hear the auditory cue right hand corner ahead. And so we had these two conditions, and we compared the findings. And perhaps the first thing I'd like to say is that pretty much everyone but one participant actually reported motion sickness within minutes. And 50% of them had to actually stop the trials prematurely due to the symptom severity. And we also had 2 incidents of vomiting, luckily one after exiting the car. But what it does tell you is that if you put people in this sort of situations, it's a very, very provocative environment. And you can almost guarantee that a lot of people will get sick in these conditions. So why this study is important is it sort of indicates the severity of the problem and the also how easy it is actually is to induce this motion sickness in these sort of conditions. So here you can see the effect of the auditory cues. So you can see a little bit of damping effect. So if there's no cues, we'll get a higher level of motion sickness compared to the auditory cues. But of course, it doesn't resolve the issue. It just has a moderating effect in that it lowers the level of motion sickness. And it was quite significant by about almost 20% reduction in motion sickness. So it's quite significant. But it was also perceived as cognitively demanding. And quite a few participants actually reported sort of tuning out, finding it too demanding, and sort of stopped listening to the actual messages. And again, coming back to the design challenge, how do we create things that are effective but also acceptable from a passenger perspective? Next, I'd like to talk a little bit more about predictability and anticipation, because there's a lot of different constructs that are sort of as part of this anticipation involved in it. And this particular study, which we've done in collaboration with TNO and Ford, the question here is, what's the impact of the predictability of motion per se? So in this case, people were exposed on this sled to 50 minutes forward and backward cosine motion. And the motion had a different condition. So at fixed intervals and in a fixed direction. So this was very predictable. At fixed intervals, but in a variable direction. So directionally unpredictable. So you wouldn't know whether it would go forward or backwards. And at variable intervals while keeping the direction fixed. So in this case, you didn't know when the motion was going to happen. So there's a temporarily unpredictability. Again, that's sort of summarized here again. So this is the predictable motion. This is the directionally unpredictable motion. So suddenly you may have a backward motion as opposed to forward motion. And here you can see the temporary unpredictable motion where the intervals between the maneuvers is slightly changed. On the right, I'll briefly show you a quick video of the facility before it was completely finished. So you can see me going up and down there on the track. In the actual study, we used a cabin that was surrounding the participants, so we wouldn't be able to see outside of the vehicle. And that's very much in line with the ISO norm, which also refers to no outside vision. So what did we find? We did find, as expected, that motion sickness was significantly lower for the predictable condition compared to both of the unpredictable conditions. So you can see that in the graph quite clearly. And the unpredictable condition led to 52% higher illness ratings compared to the predictable condition. And given the design of the experiment, we attributed this to decreased anticipation of the motion. In a follow-up study, we looked at auditory cues. And again, we used a very, very similar setup that we had before. We had the same type of movements, and we had two conditions. One was a control condition and one was an anticipatory condition. And in the anticipatory condition, the participants would receive a cue about 1 second ahead of the actual motion, whether the cabin would actually move forward or move backwards. There was also a control condition, which used false cues to control for stimulation. So some people might argue, well, you're providing cues, whether that's auditory, visually, haptic, whatever it may be, which sort of stimulates people, and that may have an impact on the actual motion sickness that people report. So this study was really set up to try to control for this and purely look at the actual effect of anticipation of the cue. And so again, just to illustrate this, the control condition we had it uses false cues to control for stimulation. So there was a cue that indicated forward or backward motion, but it was not related to the actual motion. So it either came too late or too early, so it didn't have a correlation with the motion. And of course, in the anticipation condition, there was a clear relationship between the cue and the following motion, as you can see here on the bottom. And again, as predicted, we found indeed a beneficial effect of anticipation, and the valid auditory motion cues led to a significant decrease in motion sickness, again, about similar size, so 17%. And so what it tells us really is that the effects are not the result of mere stimulation, but there's actually a cognitive process going on in which anticipation is being used to reduce the difference, the discrepancy between sensed and expected motion. So all in all, we've done a fair few studies around predictive cues, and I know that lots of other people and research groups around the world are also looking into this. And I think there's a good reason to do this, because I think what we've consistently shown, even in a real world environment, is that there's really beneficial effects of predictive motion cues. And so they might provide quite an elegant and effective mitigation strategy. What we don't quite know yet is what the relative effectiveness is of the different predictive cues. So there's questions around the modality, the timing, sensitivity and specificity, the information that we're providing, how dense that is and how accurate it is, and also how we present this information. Is this centrally presented, or can we use ambient peripheral presentation as well, which may be beneficial in terms of the actual in-vehicle experience. The other question is how their effectiveness may differ in different provocative motion environments. So in these situations, we're using sort of medium provocative environments, and we found sort of effects of about 20% reduction in motion sickness. But actually what we might find is that if we look at less provocative environments, then the effect might actually be bigger, and that it might avoid people actually experiencing any motion sickness at all. So it's another question that we have around the use of predictive cues. And as I mentioned before, a big question is whether they are acceptable from a passenger experience perspective. And that's really, really important because, as I mentioned before, the fact that it's efficient and effective doesn't mean that it's acceptable. So that's really important element to consider. And what I'd like to do next is actually look at one of our more recent study where we looked at well-being in rear seat vehicles, back of the cars, particularly in chauffeur-driven vehicles. And this was a study in which we worked together with Bentley and VW. And we were interested to see what can we do with a relatively conventional setup of a vehicle. How far can we push the boundaries in terms of making slight changes to the vehicle and see how that actually has an impact on motion sickness. So in this case, we're interested in what the effect would be in reducing acceleration levels, aligning the passenger body and head to the resulting forces. So this relates to gravito-inertial force vector. And thirdly, provision of motion cues. So in this study, we had a lead vehicle, a Volkswagen Passat, that was programmed to follow a predetermined driving profile of stop and go. And as you can see at the back, the Bentley was the following car, which included the passenger in the rear seat. And the following car actually used adaptive cruise control to keep constant distance to the lead vehicle, very much mimicking the pre-programmed driving profile of the lead vehicle. So here you can see the track that we used at Myra in the middle of England. There's two long stretches here. And the profile that we used was quite representative of real-world driving. Accelerations ranging from -3.2 to 2.7, and we had a maximum speed of 80 kilometers an hour. It was a 20 minutes drive, so we had about 8 loops along the track. And in terms of the ACC, in terms of the accelerations, we had the comfort condition and the dynamic condition, and these were series production settings of the vehicle. And what you can see here on the left, you can see the slight changes in acceleration in the two settings. We also looked at compensating for pitch, and as some of you may well know, there's some work, particularly by Golding et al., that looked at aligning people to the gravitational inertial force factor may have a beneficial effect in terms of reducing motion sickness. And of course, this is also partly the thinking behind active suspension systems, where we're looking to reduce motion sickness using those suspension systems. In this case, we didn't have the luxury of an active suspension setting, but we modified the damper setting to minimize pitch during acceleration and deceleration. And by doing that, we did change the gravitational inertial force factor and aligning it with the body. And we had two conditions here. We had the series setting, which is the standard damping setting, and then the tune setting, which is at the maximum damper current to really reduce any pitch during the acceleration and deceleration profiles. Again, here you can see the impact that it had on the gravitational inertial force factor. And last but not least, we also provided people with motion cues. So here you can see integrated into the door card of the vehicle, a strip of LED lights that either provided instantaneous motion, as you can see in the blue in the middle. So it was an optic flow pattern that moves in correspondence with the vehicle speed. If there was a braking maneuver coming up, a red cue would be shown. If there was an acceleration event coming up, a green cue would be shown. And it's perhaps easiest to briefly show that in a video shortly. But what's quite important is that, first of all, this created a sort of see-through effect. So even though it was an abstract optic flow pattern, it felt like it was one with the environment outside. So it almost had a see-through effect. Secondly, it's important that we actually didn't use an automated vehicle. So we're actually using a standard series vehicle. And so the predictive cues were based on the information that was provided via the adaptive cruise control. So we had a very limited time window where we could actually use these cues with some noise around it as well because of the system noise. And what this meant was that the predictive cues were presented on average half a second to 1.5 seconds ahead of the maneuvers, but there was also some variability in when these actually were presented. And this is quite important perhaps in the future, where we look at what are the best predictive motion cues. They probably are far more consistent with this, but I'm just mentioning this here as something to keep in mind. So here you can see the setup, and I'll just briefly show the video so you can get a sense of what people experienced. So participants were instructed to read a Kindle throughout the 20-minute drive, and at 1-minute intervals, people were asked to rate the misery scale as per usual. And in the video on the left, you're probably going to see a braking or an acceleration cue here, followed by acceleration of the vehicle, and a deceleration cue, which you can see there. Now, I have to say that the video doesn't quite justify the perception inside the vehicle, but I hope you get an indication for an idea of what the setup would look like. So in total, we had lots of conditions. We actually had 16 participants, equal gender split, 30-60 years age range, and above average susceptibility to make the experiment a bit more effective. And we used the within participant design with 5 different conditions, which is quite unusual to have 5 different conditions with people coming back for all of them. So that was quite a challenge within this project. And so we had unique combinations of settings related to the ACC, so whether it's dynamic or comfort, suspension, whether it's series or tune, and the lighting on and off. So that lighting consisted of instantaneous motion and also predictive motion cues. So if we look at the results, we can see that, as expected in all conditions, motion sickness was rising consistently. And after the end of the drive, motion sickness also dropped very quickly, with some participants, of course, dropping symptoms earlier than others. But what we also found, to our surprise, is that the actual impact of the ACC and suspension didn't have any impact in terms of the motion sickness compared to the control condition. What we did find is that lighting effects did have an impact on motion sickness, particularly later on. So from about minute 12, 13 onwards, 15 onwards, it really seemed to make a difference. But what perhaps was most surprising is that we actually found quite a big effect of the wellness pack. So where we combine all these things together. So we looked at reduced accelerations, we tuned the suspension, and we provided the lighting cues. That really led to a reduction in motion sickness, as you can see here. So here you can see the difference between the control condition and the wellness pack. And we found a reduction of motion sickness of 28%, which is very, very significant. What's also interesting is that some of the conditions actually led to reduced eye strain. So participants' task, just to remind you, was to read the Kindle throughout the drive. And what we can see here clearly is that in suspension, lighting, and wellness condition in particular, there was quite a significant change in eye strain. We don't quite understand why this was happening, but it's really interesting to note, because I think it might have potential for follow-up research and trying to understand what's really going on here. So upon reflection for this study, at least, is, as I mentioned, the reduction in eye strain is an interesting by effect that we didn't necessarily expect to see. And it would be really interesting to follow it up with some more research. The acceleration suspension levels were insufficient, but the ambient lighting created a positive effect. And as I mentioned, the mitigation strategies combined in this wellness pack had a really large effect on the level of motion sickness. And this in itself raises quite an interesting question from the perspective of how we conduct our research. How do we test these different intervention and mitigation strategies? So although some of these individually didn't have much of an impact, when we started to combine all these together, there seems to be some sort of interaction happening possibly that led to quite a significant decrease in motion sickness. And what this means really is that we need to think about the implications for the design and the evaluation of HMI concepts related to motion sickness. And we need to, where possible, keep in mind this holistic experience that people may have inside the vehicle. And that also brings me to the final section of my presentation today, and that's based around common protocols. So I am sure you're all familiar with the international standards, and a few months ago, actually, we published a paper in SAE special issue on motion sickness, in which we actually point out some of the principal research questions that we need to think about, but also the need for common protocols. So first of all, I want to talk a little bit about the shortcomings of the current ISO, which again, most of you are probably familiar with. We've got to remember that this standard has been developed for seasickness, so looking at vertical motion, has not been validated for horizontal and rotational motions or any potential interactions between those different axes. So there's still a lot of work to be done to understand whether the frequency dependency is the same, different, and importantly, also whether it may differ for different measures of motion sickness. So the current ISO is derived from the percentage of passengers actually vomiting or reaching emesis. But of course, as we know, for our purposes, the research that we're doing, we're not interested in the endpoints of motion sickness, vomiting. We're really interested, particularly in the lower levels of motion sickness. Early symptoms and signs of motion sickness are particularly important to us, because we believe that the vehicle experience very quickly deteriorates as soon as we start experiencing symptoms. And of course, also the impact of the motion, the impact of modulating factors may be very different for lower levels of motion sickness compared to the ultimate level of motion sickness called vomiting. So there's work to be done in trying to understand whether findings and the assumptions of the current ISO are still relevant and valid for other conditions and lower levels of motion sickness. And of course, another element of the shortcomings is that at the moment, the modulating factors that we know have an impact on sickness, they're not included in the current standards. So that relates to things like vision, anticipation, passenger orientation, and also reclination angles. So another element is that the protocols that are provided within the ISO are quite limited, and they don't really provide sufficient guidance for people to actually take it on and move forward. So we believe there is a real need to actually develop something together so that the whole community of motion sickness research can actually have some sort of common denominator to really accelerate our understanding of motion sickness in these different environments, whether it's augmented reality in cars, car sickness, and all the related elements. So we think this is very important. And just to give you one example here, this is some work that was recently done by Anna Reuter, working together with Jelte Bos. And she was comparing scales that are asking for unpleasantness. So for example, the fast motion sickness scale, or symptomatology. So rates, scales like the misery scale. And what she found, she plotted the symptom progression, like the MISC scores, against the unpleasantness ratings. And what she found is that there's a discrepancy here. So what we essentially find is that the beginning of nausea in the misery scale rating is being perceived as less unpleasant than higher levels of symptoms such as headache, dizziness, eye strain, etc. So we can see there's a discrepancy between those two measures, and this is really important because one doesn't imply the other. So unpleasantness can be predicted based on symptom progression, while the progression of symptoms cannot be predicted based on unpleasantness. And so it's really important that we are aware of these sort of effects and that we take a common approach to measuring symptoms. So in addition to that, there is still a need to also think about identification and development of appropriate vibration measurements and motion sickness assessment and evaluation methods. And we believe that it will be greatly benefit our efforts to mitigate motion sickness. And on that note, I also like to use this opportunity to call for participation, and particularly related to the international standards. So we now have a preliminary work item agreed. And so we are now looking to actually for volunteers to work together on the development of a new standard. So if anyone is interested, please get in touch with me. I'd be very interested to speak to you. And finally, related to this, there is still an open call for a special issue, whole body vibration of the MDPI journal, in which we're still looking for papers that are looking at the limitations of the current standard. So with that, I'd like to thank you all, and I hope it was of interest to you, and I'm happy to take any questions.
Okay, thank you for your interest talk. Okay, so any comments? Is the question? No? Okay, so I have a small question. So sometimes you show the result of the level of the motion sickness. So for example, page 24.
Yeah.
Yes. So I missed this. You were talking how to measure the ratio of the level of the motion sickness now.
Yeah, so is that we're using subjective ratings of motion sickness, because these have been used consistently and validated across very many different environments. And so we believe that that should be the cornerstone of any motion sickness research. If that answers, are you referring to using alternative measurement tools as well?
Okay, so now the period of the experiment about that 20 minutes. So I think this 20 minutes so too short for the motion sickness. So usually the user can feel the motion sickness for long driving. So but your result is after 1 or 2 minutes level of the increasing. So how heavy the motion sickness level of the maximum? Maybe the 4 or 5 is the maximum ratio now. You are in your result. How heavy the 4 and 5?
Yeah, I mean, this is partly based on our ethical protocols. So we stopped the trials once we reached level 7 on the misery scale, and that's just to reduce the level of discomfort for the passengers. But what we can see very consistently is that if you look at even the different studies that I showed you now, they all have slightly different conditions, but what you can see is very consistent is the way motion sickness increases over time. And if you would overlay all those different graphs, they actually very much show a very, very similar pattern. And what I also should say is that particularly in those situations where we have in-vehicle activities, motion sickness actually happens very, very quickly.
Okay, thank you. So any questions? Okay.
Thank you for the presentation. It was very interesting. So I have a question regarding the part when you talked about the predictive cues inside the car with these like green, blue lighting and stuff. So I was wondering so first of all, I was wondering if the predictive cues made the people to stop reading the Kindle, or like have you monitored that? Or if not, like, what do you think about like just the existence, merely the existing of the predicting cues help with the sickness, or is it that they kind of like cue the people to stop doing what they're doing or stop doing some activity that actually induces sickness? Thank you.
Yeah. Well, can I just say that that's a really, really good question, and it ties into some of the things that I mentioned. So first of all, in terms of the actual reading task, is that we controlled people for reading in the sense that we made sure that they didn't look up. So at all times, people are still reading, or at least looking at the Kindle. That's not to say that they were actually reading, of course. So what we didn't have any eye tracking, for example, incorporated into the display that would then allow us to actually say, well, are people reading or not? So that's one way of controlling for that, or having some sort of talking out loud protocol, for example. So we don't quite know, and but what I do know is that people have been looking down at all times, so they didn't look up. But I think in combination with the studies that I showed on the slide, we did show that there's a clear cognitive impact of predictive cues. So it's not just the stimulation. So we know it has a cognitive impact, which leads to reduction in motion sickness. But the other question, which is related to your question, is how can this possibly be used to help people manage motion sickness themselves? So, and I think this is what I mentioned before. We haven't quite worked out. It's one area that we haven't explored is self-management of motion sickness. So how can we help people to, particularly if we know that they are susceptible, how can we help them to prevent them from getting sick by helping them and providing cues saying, hang on, at this moment, there's something happening, it might be better to look up, look out of the window, or stop doing what you're doing at the moment. And these sort of active interventions are really interesting. And they're also related to the real-time monitoring of people's progression of symptoms and signs, so that we can actually adaptively have mitigation strategies to help reduce motion sickness. So it's a good question. Yeah, thank you.
Other question? How about online? Roy-san.
Yeah, sorry, you might have mentioned this in your presentation, but maybe I missed it. This motion sickness, how comparable is to have the car motion sickness and a personal mobility scenario motion sickness? Or maybe my question is, do people in personal mobility vehicles or smaller vehicles also get motion sick? Or does it have to do with velocity?
Yeah, what do you mean by personal mobility, particularly?
Like a wheelchair type of vehicle or smaller,
Ah,
like one person vehicle?
yeah, yeah. It's a really interesting question because one of the areas that we are doing research into is future alternative vehicle topologies. So we believe that in the future we'll have a wide variety of type of vehicles. So it becomes a really interesting question. I think it all starts with the actual motion profile. So if it's very often we get the question, yeah, but what about trains, for example? Why do people don't get sick in trains? And of course, the answer to that is that the acceleration profile is very different from a normal passenger vehicle. And so I would say the first answer to that question for me would be it depends on the motion profile that's being experienced within that vehicle. But I think if that motion profile itself is the same, independent of the type of vehicle, then I don't expect much of a difference in actual motion sickness. So it can happen across different vehicles, provided that the motion is actually sufficiently provocative to actually create motion sickness.
Okay, thank you.
Thank you. So, any questions? Okay. Okay, so the time is up with this workshop. So Cyril, thank you for your presentation again.
It was a pleasure.
So, so it's time to start the next other workshop. So, okay, so we have no time for the closing. Say something? So see you next year, the workshop. Thank you for attending this workshop. And so we had a very active discussion. Thank you.
So, hello. Thanks for being here. Thanks for joining us in this first workshop on extended reality for smart production. And also thank you for preferring our workshop instead of the social program. It's the first workshop ever on this topic here on this conference, which is an honor for us, of course. My name is Josef Wolfertsberg. I organized this workshop together with Thomas Moser. We are from University of Applied Sciences in Upper Austria and St. Pölten. And we had, of course, many submissions to this workshop. And we decided to take 5 papers from Austria and Germany. So we have a very strong Central European focus today. And we won't lose any time anymore. I suggest to start with the first presentation by Horst Orsulic from University of Applied Sciences Technikum Wien. He will present to us remote today. So I hope everything works.
Good morning from Vienna, or good afternoon from Vienna.
We hear you. Perfect.
That's great. I hear myself as well. I mean, we have a backlog, but that's okay. That's okay. So, hello, everybody. Warm greetings from Vienna. My name is Horst Orsulic. I'm from the University of Applied Sciences, Technikum Wien. And I'm going to start right away with the presentation. Once I got the screen sharing up and running. Great. Now that the technology is solved, I'd like to welcome you to my presentation with the topic of using mixed reality-based digital twins for robotics education, which we evaluated and investigated together with a group, a research group here at Vienna with Sebastian Rau and Jose Garcia and myself. We are running a research project called Integration of Virtual Systems in Lecturing. And as we have a strong background and also study courses, bachelor master's degree on robotics, this is one of our research interests. How can we use these technologies, especially augmented or mixed reality, for accessing and also leveling up the understanding of robotic principles at the very beginning. The International Federation of Robotics predict that in the next 10 years, roughly 50% of production operators are going to work on shared desks or at least common workplaces together with robots. So we need to pick up those workers and operators and level up their skills of understanding and cooperating with robots. And future engineers are going to have increasingly connected systems rather than discrete machines. And also they need to understand collaboration and connected systems between machines and humans. So IoT, industrial IoT, is going to play a central role towards the Industry 4.0 or 5.0 actually domain. And our approach based on these insights is to develop a mixed reality application for leveling up this understanding or close this gap. Why is that? Well, for industrial robotics, especially industrial robotics, articulated robots, it's a quite complex system. We have one of the more complex mechatronic systems where we have a lot of coordinate systems to deal with. It's a serial kinematics chain with 6 degrees or more of freedom. And students need to understand how this system is built up and how each axis works to sum up a robot path, for instance. So the forward and inverse kinematics is quite a challenge for them to understand. They need to have a spatial awareness, as we have 6 degrees of freedom with 3 translational and rotatorial degrees of freedom. So it's a kind of a challenge to understand what's going on in robotics, let's say it that way. And as we all know, transferring from 2D into 3D space is kind of a challenge, and a lot of teaching and explaining is done from slides and books and videos. And also, of course, on the robot itself is the best training, as literature proves. But not every university or every study course can afford an industrial robot. So transferring from 2D to 3D produces cognitive distance, as we have to gather the 2D information and transfer it into 3D space, especially for spatial challenges like coordinate transformation, path planning, movement in 3D, and programming a robot in 3D. These are particular challenges. Probably you're familiar with this example. This explains it best, what cognitive load means or cognitive distance means when we drive with the car and using our navigation systems, Google Maps, for instance. We need to transfer 2D information into 3D space and need to find out which is the next crossing where I need to turn right. So if we could use extended reality, mixed reality, augmented reality, whatever, directly superimposing us the necessary information into the 3D space, we are not producing that much of cognitive load. And we can focus and use our capacities on the actual challenges we have to accomplish. Now, there is a variety of definitions and ongoing discussions on where is augmented reality and mixed reality and the borderline in between. There is a very good survey from Rauschnabel et al. From this year, where they did a survey of 67 papers dealing with these topics. And they figured out there are 4 dominant views in literature. present, and they suggest that at the beginning of a scientific discussion, it's important to agree on one view rather than discuss what is augmented or what is mixed reality or what is extended reality and so on. So these are the dominant views: MR dominant, VR dominant, MR centered, or extended reality. And they suggested then also an X reality framework. To sum it up, we are going to work with the MR dominant view. So where, let's say, everything towards the real world is augmented, and in the center, we are working with mixed reality. A short question on the side. I see pop-ups for waiting rooms suggesting me to let the people in. Is that my task, or is there somebody attending this?
No, it's definitely not your task.
I'm just asking. Maybe I could just, okay. Great. So, as well as a heavy discussion is going on, where is AR and MR, there is also a lot of investigation and research going on how to use these technologies. Recently, we see that mixed reality and augmented reality are more and more used in classrooms and lab exercises. So there is increasing development going on, there is increasing research going on, and solutions start to come up, mostly based on the survey of ACCHAR and ACCHAR in K-12, so high schools, and only 30% of the identified examples using AR for or MR for education are in universities. So that motivated us to start with our own developments towards this direction, and we came up with an AR app for robotics education, where we hand out QR code to the students. We did this with PTC software, so it's called ThingMark, and we superimpose a CAD model from an industrial robot, which we also use in the lab, so the students can learn on their own time and pace fundamentals of robotics, to show the coordinate information, coordinate transformation basics. They can operate this robot in the simple axis. And we first did this approach by just using a mixed reality application or an augmented reality application, and to identify whether students stick to it, are going to use it, and how they come along with it, and how the feedback is designed. We did that in a survey with roughly 50 students to find out, are they going to use it? Do they use it? And what's the benefit out of it? So towards motivation, of course, as literature also proves, it enhances the motivation, and in their opinion, it enhances the way how they learn robotics, and those results motivated us to go to the next step and introduce the augmented reality robot number 1, where we decided to do a virtual product development approach, to use digital models first to evaluate and decide certain steps along the development. Together with students, we did this project, where you can see here a first design example. We already had the connection from the motors. We decided to use smart servos to have sensor feedback. We are getting the temperature, the actual current, the angle position, and the voltage out of each motor, and we connected that up and hooked it up to an Arduino. And the CAD model was already built, and then we used an augmented reality, this time in Unity, to get a first impression on the actual robot when we're going to build it. These are 3D printed parts, and we had a chance to evaluate the behavior already of not just the robot, but also the digital twin idea as a fundament of this work. So a digital twin definition from our point of view is when we have a real asset and a digital asset or digital representation, and both of these are interconnected with each other and capable of transferring data in both directions. So not only having a CAD model or a connected CAD model or connected system of such a real asset, but also be able to use the digital representation to gather information, or in our case, to showcase or to view the digital model and operate the real model using the digital model. As you can see here in the example, we're applying a load on the 6th axis of the robot, and we can use the digital representation in mixed reality to highlight where is the torque rising and where is the torque reaching a critical limit at which axis. So that to help understand the complexity of a 6-axis articulated robot. And to showcase this also in class and in demonstrations and at fairs and so on, we built the Arno #1, the augmented reality model #1, as a mobile platform, as a desktop size robot for several reasons: low cost, easy to transport, and easy to showcase and demonstrate. The potential for digital twins and the potential for using mixed reality in robotics. So as you can see here, as demonstrator for digital twin, we have a Unity application where we're able to control each axis with a slider directly. And we can show the current sensor data and use these to update the mixed reality model to follow the behavior. We can superimpose additional information from the servo motors, like current angle, current, and so on. But we figured out that using Unity, using a Raspberry Pi and Arduino is sufficient for demonstrating it, but not sufficient when it comes to industrial robotics or understanding of industrial digital twins. As we have a direct connection, or had a direct connection, between the Raspberry Pi with ROS and the mixed reality application in Unity, there was almost no latency. But when we transfer that to industry-related cases, which is we are in the faculty industrial engineering, so we have a strong relationship with industry, and we are educating our students towards industry applications. So the next step of the development for the platform was to kick out the Raspberry and Arduinos and introduce industry PLC to the system. Also, we did a redesign of the robot, and we formed the platform Arno 2. Very creative name there. But we used the B&R PLC, capable of solving inverse kinematics for robotics. So it's a proper PLC for robotics and robotic problems. And we used a cloud architecture from PTC called ThingWorks to build up the digital twin and the digital twin fundament for the application, which resulted in the current version of the system, where you can see the CAD model here for the industrial robot, we had pretty tough calculations to come up with a quite solid and stable solution of this desktop robot. Spoiler alert, I cannot answer any questions towards costs so far, as we are calculating the manpower, because it was the first prototype, but we are thinking of probably doing several more of them. So you can see here now the movement and the behavior of the robot itself and the size. Here again, it's portable, it's easy to bring into class. We have several classes where our robot lab resources are limited. So we can use this system additionally. And now you can see the mixed reality application where it is possible to control each axis again and send these axis information to the robot controller. So we have direct axis control for each of the 6 axes, and we can see this superimposed information of the current angle, and we can switch these again to current, voltage, temperature, and so on. So again, vice versa communication, we can directly control the system and directly gather information from the system. We're using UART for the communication from the PLC to the servos. We're using OPC UA as the fundament for industrial IoT or Industry 4.0 communication so far. And then we use the PTC infrastructure we built up with ThinkWorks and the CAP server to form the basis for the digital twin. And in the final step, as we wanted to figure out how far we can push the PLC actually towards kinematics and inverse kinematics in particular, so that we can do a path planning. We did another master thesis together with a mechatronics student to come up with path planning. And once you have the inverse kinematics and the path planning possibility, you can also superimpose the work envelope of the robot, which you can see here. And we can use the tablet or the mixed reality application now to directly program a robot, because X-wise control is good for understanding which axis is what and how does it move. But for programming a robot, you typically use path planning algorithms and do not directly control the axis. So what you've seen now is that we can identify whether the path point is within the work envelope or not, and then speed it up process. We can do the path programming, send the whole path programming to the controller. The controller calculates the inverse kinematics for each position, and we can additionally show the digital twin next to the robot to gather, again, inside information on the behavior of the system, on all necessary values of the system. But what we can also see, I don't know how fluent or how good the video quality is in Singapore, but there is a delay between the digital model and the real model, which is not due to Zoom call, it's due to the cloud architecture of the actual application. This is also something we want to evaluate in the next step, how to improve communication and the data model between the PLC, the cloud architecture, and the mixed reality application, which is the setup several industry partners have as well, and they're dealing with the same problems. Or if it is necessary to have all information at time, or if a certain delay is acceptable. To sum it up, the whole project is ongoing. We started to evaluate and compare the Arno system within our robotics lab with our students in the first and second semester. to find out pros and cons for the use, and also how the mental effort, we are going to use NASA TLX for that, how the mental effort is between both programming situations to identify possible next steps where we need to improve the systems and so on. So we've developed a showcase demonstrator to also show the concept for digital twin as well as a mixed reality application itself for robotics and robotics education. We have a low-cost solution for practical training and teaching in class. We do this also with industry partners to have to visit them and just pack our stuff and bring it there, which is quite easier to transport than an industrial robot. So we have a low entry barrier for teaching there, as the system itself is desktop size. It's 24-volt based, so there are no risk and safety regulations to take into consideration. Nobody can harm himself, which is also an aspect we're investigating towards how respectful and how the fears are for students to operate an actual industrial robot, even if it's in lab, compared to a desktop size one. And we can certainly improve and further develop the mixed reality application to show more data, to enhance the control of the robot and the path planning. Finally, literature. Thank you very much for your attention. I'm pretty good in timing, is it right?
Perfect.
Excellent.
Thank you very much, Mr. Horst Orsulic. Are there any questions from the audience? Any questions? Online? Okay, can you provide a bit more information on how you integrate your approach into the current curriculum of yours?
Yes, so we are working together with our colleagues who teach robotic fundamentals, and they are equipped with a slide deck and a tutorial for the mixed reality application. And then when they are using it in class, they have one session of 45 minutes or something, where they showcase it, and then students can try and work with Arno. And we coordinate that with, or we are going to coordinate that with one of my colleagues, with Sebastian, who is on the front slide, to do the according survey with the students. So we have a questionnaire, and we're going to hopefully get some more insights on how students feel with the system. Of course, we are huge Arno fans here, but we need to find out if the students are as well.
Thank you very much. Any more questions from the audience? Yes?
Hi, this is Zoe from Singapore. Thanks for your good presentation. I have two questions. One is compared with a traditional robotic simulation, how this AR, VR type of robotics compare with the traditional robotic simulation? I believe you need to invest more time, more resources to build up your AR model. So from the learning point, is it much better compared with the traditional robotic simulation? Secondly is just now from a lot of video, we're able to see some experiential enhancement, so people can play, but it will be definitely better for learning purpose. If you're able to, for example, display the drawing angle or some of the number, so the student can more appreciate how it linked to the kinematics, especially when we talk about the robotics. Yeah, thanks.
Thank you very much. Excellent questions. For your first question, we decided to go with our own development. Yes, there is a certain more effort, but as we started with the ABB model, And we wanted to show some inside information on how a robot is built up, where the motors are located, how a drivetrain is built up. We didn't get that CAD information from the manufacturer. So you can get a CAD model, but it's only the outside. So they don't give you, or at least we didn't get a full detailed CAD model. That's why we decided, on one hand, we decided to use, or we develop it on our own. Also, we wanted to investigate, because our students are quite capable of developing and I would say, building small-sized robots. We wanted to investigate with a systematic approach on how well they could develop that and use it with a mixed reality approach to explain what went on. So that's why we decided to take the effort. You are right. When it's possible to get the full CAD data from an industrial robot, we would have chosen that way as well. And for your second question, if I got you right, that's in the current phase of the next development step. We are using superimposing of coordinate systems at each axis, and to coordinate transformation from each axis to the next to solve the forward kinematics, and especially show the necessity or specialities of Denavit-Hartenberg, which is a convention to simplify the kinematics. This is current state. So we are showing them the matrices information, the matrices multiplication. We're superimposing the coordinate system on each axis, and that's definitely on our roadmap for that. Did that answer your question?
Thank you very much. Yes, it did.
Right.
So thank you, Mr. Orsulic. I suggest to move on with the next presentation. You will stay online?
Yes,
Mr. Orsulic?
definitely.
Perfect. So if you have any more questions, please use the chat function.
Yeah.
Thank you.
Thank you very much. Thanks for having me.
Thank you. Thank you. Next presentation will be by Jana Podkozova. I hope I pronounced it correctly, more or less. She will talk about point cloud to BIM registration for robot localization and augmented reality. Yeah, of course.
Okay, thanks. The general context of this work is building information modeling of BIM. That's a concept that involves processes for digital representation of structure and functions of buildings. And essentially, a BIM model is a 3D model and some metadata. So here, for example, is a BIM model of the library at Wien. And you can see a selected element, a column, and here on the right you can see all sorts of information about it, what type of material it uses, whether it's load-bearing or not, and so on. And these days, all new buildings are supposed to have a BIM model associated with them. And in the paper that I'm presenting, we address a very specific problem about BIM. And this problem is if we have a BIM model and if we have a point cloud scan of an environment that this BIM model represents, how do we spatially match the two? Or in other words, what is the transformation from the coordinate frame of the point cloud scan to the coordinate frame of the BIM model? This problem is relevant to several applications, including BIM. If we want to do automatic comparisons between BIM and buildings, we would need to know how they spatially match. If we use an autonomous robot for certain tasks in buildings, for example, automated inspection, we'd need to know at every moment where in the building and in the BIM model the robot is. If we use augmented reality for maintenance and control, for example, again, we'd need to know how the model and the building match to be able to display augmentations at the correct position. And this research is done within a project BIM check, the main goal of which is to find deviations between buildings and their BIM models in terms of geometry and installations. And further goals are to improve construction documentation in different stages of construction and to improve real-time sensor localization. So in our target system, we have a LiDAR scanner. We have mounted this LiDAR scanner in two ways. We have a handheld setup that's held by a user, and there is a laptop on which a user can see the output. The other setup includes a Boston Dynamics spot robot, and the LiDAR is mounted on top of it. And the sensor produces this type of output or input for our process. So it's a collection of scan points that are centered around the sensor position. The scan points are used in slant tracking process that produces a larger point cloud map and the sensor pose within it. Then we have the point cloud map, we have the BIM model, we perform our registration procedure on it, and we get the transform from the point cloud to the BIM model, so we have them matched spatially. And the system is implemented as 3 independent components that talk to each other via TCP messages. The real-time data and tracking component takes LiDAR input, runs SLAM on it, and outputs a sensor pose and the point cloud in every frame, and this data is available on the server interface. Then the localization component takes a BIM model, we use the IFC format. It requests the point cloud from the tracking component and runs the registration on this data and produces the point cloud to BIM transform. That's also available on the server interface. And then we have the visualization component that loads the IFC model. It requests the sensor pose, the current point cloud from the tracking process, to transform with them, for them from the localization process, and it visualizes everything in Unity. And further in this talk, we'll focus on the registration component. So the very basic idea behind our registration approach is to convert the BIM model into a point cloud and to register 2 point clouds together using iterative closest point algorithm. It's a method that minimizes the distance between points. But ICP is a fine-grained registration method, so it needs a sort of initial guess to work well, or a coarse estimate, and we use template matching to obtain this coarse estimate. Our registration happens in 4 big steps. So the first step, the BIM model is voxelized or converted into points, and at this point, the point cloud representing the BIM model and the scan point cloud are at arbitrary location, translation and rotation in respect to each other. And the next step, we align the scanned point cloud along the coordinate axis of the global frame. Then we do template matching that produces the coarse transform estimate. And finally, we run ICP that gives us the more fine-grained registration. At the voxelization step, we use IFC OpenShell library to load the model into the project as a C++ object, and the voxelization toolkit that actually splits it into voxels, into discrete representation. Then if the BIM model contains multiple flows, we manually select one that we're operating in. We can do this through the visualization component, so through a configuration file. And the main parameters here, parameter here is voxel size, and we usually use 10 centimeters. The main goal of the next step, axis alignment, is to align the Z, or the up axis of the scan point cloud, with the Z axis of the BIM point cloud. So generally, the Z-axis of the scan point cloud is pointing in the same direction where the sensor was pointing at the start, so up the sensor. And if we start scanning when the sensor is tilted, so then the whole point cloud will be tilted in respect to the global frame. So we start with estimating the normal for each point in the scan point cloud with principal component analysis. And then we find rotations around coordinate axis by aligning as many normals as possible to be parallel to coordinate planes. And here we use the fact that most geometry in the environment will be floors and walls, so surfaces that are perpendicular to each other, so the separation will be possible. So we do these rotations first around Y and X axis to align the Z axis to point up, then we rotate around the Z axis, and then we do another pass around Y and X axis to remove any residual rotation in the Z axis. And after this step, the point cloud scan is pointing up with its Z axis, and the registration problem is reduced to 4 degrees of freedom. So now we need to find the Z rotation and the XYZ translation. And we do this with template matching. The general idea of template matching is to take a template image and find its position within another source image. And we obtain those images by projecting our point clouds, the voxelized one and the scanned one, along coordinate axis. We start with a up projection. This is the top projection of the beam point cloud, and this will be our source image. And then to find the matching, we project the scan point cloud also along onto the XY plane, and we try every rotation along the Z-axis. So we start with a 0 rotation, we take the top projection. This will be our template image, we'll do template matching. Then we rotate the scan point cloud by 1 degree, here you don't see it, but it's rotated, do the template matching again, and we repeat it, rotating the scan point cloud again and again until we make a full circle. And then in the end, we'll take the best template matching result, and this will determine the rotation and the XY translation for the scan point cloud. And after that, we only need to find the translation along the height axis, and we'll do this by projecting onto XZ and YZ planes and taking the average template matching result. And template matching that we use is implemented in OpenCV. One important feature of our template matching implementation is that we only take points on the surfaces that are perpendicular to the projection plane. So we do normal filtering for points. For example, for XY projection, we'll only consider points that belong to the walls. And here you can see a comparison. This is the top projection without normal filtering used, and this is with normal filtering. So you can see on the lower images, we can detect the outlines of walls much better, and this improves the performance of template matching a lot. And the final step of our registration approach is ICP. We use a point cloud library implementation. We use a variant with a random subsampling of the scan point cloud. That means that we don't match every point from the scan, but we randomly select, I think, every 50th, and repeat this in certain number of iterations, also probably 50. And these two parameters, the subsampling rate and number of iterations, can be manually configured. And that's it. That's how our algorithm works. We evaluated its accuracy in 2 test environments. One is a hallway in our lab, and we have a BIM model of it that was created from a photogrammetry scan. And another one is one floor at Tuvin Library. You saw its BIM model in the very beginning, and we scanned along this hallway loop that you see goes around the whole floor. To conduct the evaluation, we first collected ground truth sensor positions at the start of the scan, and I'll talk about this later. And then we recorded raw LiDAR data. That's how such recording looks like. So we use an Ulster LiDAR scanner, and then it's possible to record raw data in a special PCIP format. And that's what it looks like. So essentially at every point you can see the points centered around the sensor. And we can take these recordings and feed them into our data and tracking component, just as we would use live data. And then every time the SLAM process creates a new keyframe, we add a new portion of the point cloud, so the current frame offset corresponding to the sensor position to our data point cloud. And then we evaluate the registration accuracy at every selected SLAM keyframe. That's what it looks like for the library environment, for example. This is the portion of the environment that was scanned by keyframe 6, and this is 12, 18, 24, 30, 36. So you can see that the point cloud grows. And we do this to evaluate essentially the fit between how many points we need to accurately match the scan to the correct position within the whole floor plan, and also to evaluate the impact of the SLAM drift when the amount of points grows. To collect ground truth, we use the fact that the origin of the point cloud will be in the first keyframe of the SLAM algorithm. So if we start the sensor in the static position, that's where the point cloud 0 would be. So we put our sensor somewhere close to a wall that can be, or a corner that can be easily recognized in the model. We measure its real world position. Then we replicate its position in the loaded model in Unity, and like this we can see, we can determine its global coordinates in the beam frame, or in the global frame. And then the registration is supposed to bring the origin of the point cloud into this point, and by comparing these two positions we can calculate the error. So we collected 10 recordings, each for hallway and for the library corridor. There were different amounts of keyframes in it, so there were different length and amount of points depending on how quickly we move the sensor. Here are the results for our hallway. Well, here the registration worked from the first keyframe, so even if we had a very small portion of the environment scanned, it registered correctly. By correctly, I mean that the error was smaller than 1 meter. We see no apparent trend in error. It doesn't increase or decrease with the amount of keyframes. And here the average error in XY plane was 3 centimeters, along the height axis 3.7 centimeters. In the library corridor, the results were more complex and mixed. First of all, we noted that matching step didn't always work correctly, especially depending on the starting area. We started, for example, when we started an area that's marked with A1 in the lower part of the corridor, and when not so many points were collected, it would get matched to a wrong portion of the environment because of the self-similar structures in the floor plan. But as we collected more data, then this matching was reverted to a correct position. So here we saw that from about keyframe 28 would reliably match the point cloud scan into the correct position. Another thing that we noticed was a rather large slam drift as more points accumulated. So here you can see that the lower part of the corridor is not parallel as supposed to be. And on the top part where this portion of the staircase is, you see the blue points that correspond to the current sensor frame in this recording don't fit to the original position. That's fixed by loop closure in SLAM, but not all environments can provide loop closure, and we did not evaluate it in this time. So these are the results for the hallway loop. You can see here that the error seems to increase, especially in the right part of the graph when the sensor traveled up to 80 to 100 meters. If we average the error in a rather in the flatter region, like up to keyframe 36, then the average error in XY plane is about 20 centimeters, and along the Z axis about 25 centimeters. Here we saw that in this complex environment there were two major sources of error. First, it's the self-similar structures that sometimes contributed to wrong localization when only a small portion of the environment was scanned. And another source of error is slam drift. And now we're able to compensate to a degree to slam drift. That's not in the paper, these are very new results. So instead, at ICP part of the algorithm, instead of using all the point cloud, we take about the first keyframes. And this results in much better matching performance. So these graphs show the results averaged between the hallway recordings and between the library recordings. So it's all data collapsed together, but you can see that especially in the first 20 meters, the error is reliably around 10 centimeters. And even on the longer recordings, so where we saw the large influence of slam drift before, we see the error is definitely below 15 centimeters. And to conclude, I'll show you a little video of live performance of our localization algorithm. So here again, we tested in our IT2 library. Here the LiDAR is mounted on a spot robot. There is also a small computer also mounted on the robot, and this computer is running SLAM, accumulating data, and the laptop is running visualization and localization, and they are on the same Wi-Fi network. Oh, there is no sound, that's too bad. So you can see as the robot walks, the sensor position updates somewhat slowly because the laptop was on battery power, and then it makes rendering slower. And I even have little live demo here on the recorded data. So that's our tracking component that runs like on a rather small recorded PCAP file in our hallway. It will run in a loop so that we keep seeing the points coming. Here we start the localization component. And we start the visualization. Now the BIM model is being loaded into Unity. So here you see, I don't know if you're able to see the points. So at this point, the BIM model is loaded and the points are getting streamed into Unity as well. But the localization didn't run yet. So you see there is no correspondence between two models. So we could localize. Now localization is running. Here, at this point, the BIM model is getting loaded into the localization program. Now the template matching is finding the best matching angle that's found, and well, that's a debug view of the registration. And here now we see that the points are localized, and here we can see the augmented reality view. This recording was created with a handheld setup, so you can see the robot flying, but maybe they'll introduce this with the next evolution of this Boston Dynamic robots. And that's it for me. Thank you. I'll be glad to answer any questions.
Thank you. Thank you very much.
Okay.
Thank you very much for the presentation, and also a big thank you for this live demonstration. Are there any questions in the audience? Yes?
I do.
So can you go to the template matching slides? So is this images? Are these just images?
Are you finished with the question? No.
So yes, the template matching itself, the algorithm works on images. How we create them, we have these point clouds. We project them onto coordinate planes, and then we rasterize this projection. So we take a certain pixel size, like 10 or 30 centimeters, depending on the stage that we're using. We have two passes. And then each pixel value will depend on the number of points that were projected into this pixel. So in the end, the template matching itself, the algorithm is run on two images. And we do this really many times for different projections.
So that you do the template matching by the convolution, right? And
to be honest,
wait. And also that you mentioned that the Z rotation. So is the Z axis? So is the Z axis just the Z axis of the LiDAR itself? So if the robot just fall down and then the Z axis change and this method failed, is it?
Excuse me, I'm not entirely sure that I understood you. Maybe I just repeat about the Z-axis. So before we start template matching, we already performed another step, axis alignment, and in that step we made sure that the Z-axis in the source point cloud, so in the voxelized beam, and in the scanned point cloud will be pointing up. So they're parallel to each other. That's already taken care of. And here we just see how to align them is in the horizontal plane by rotating around the Z-axis. That's why we try all the 360 projections, each one at 1 degree step. So that's how we solve the Z-axis. We made sure it's aligned before, and here we find the rotational on the z-axis, and it will also give us the translation into this horizontal plane.
Thank you very much. Are there any further questions? Yes?
Yes, thank you for the very interesting talk. I have a concern maybe about the difference in the level of detail of a BIM model and the real world. For example, if you have HVACs, so pipings and so on in the real model, could you elaborate a bit about this?
So that's actually part of the... there's things like... Wait, hang on. HVAC, that's the holding construction right on top. Because I've now worked with in another project that also deals with BIM, but from a different perspective, and I've heard a lot of HVAC. So in this specific project, we're not focusing specifically on HVAC. So what we're focusing on is, well, geometry and installations in terms of pipes. Also, things like light switches and power outlets. The smaller things, but so the smaller things are going to be detected with different methods, more like with image analysis and with machine learning. We have a partner actually at in FH St. Pölten who is working on this part of the project. Thank you.
Thank you very much. We're perfectly in time. I suggest to move on with the next presentation. Thank you, Jana.
Thank you very much.
The next presentation will be by Linda Rudolph, Technical University of Munich. She will talk about human-centered augmented reality guidance for industrial maintenance with digital twins, a use case-driven pilot study.
Yes. Okay, I hope the energy will be enough for the talk. Thank you for inviting me to this workshop, which is a chance for me to show a very early step of a research project. And so, excuse me please that the functionalities might not be so advanced, but I want to focus here more on the requirements engineering process for augmented reality in industrial use cases. And I have a very special use case here today for you, which is the chemical industries. And the maintenance in the chemical industries. And as you might know, maintenance was already called a very interesting use case for augmented reality in the 90s by the famous paper of ISMAR. But specifically for chemical industries, this use case is very, very important because the corrective maintenance is a process that costs a lot of money, because if you have to shut down a plant because something went wrong and the pump is broken or so, then they have to stop producing. And the other problem is that this incidents can even cause damages on the plant when some materials become solid inside of pumps. So the chemical industry is very motivated to use every innovation they can use to enhance their processes and fasten the maintenance processes. And so we worked in a collaborative project with the mechanical engineering department at TU Munich to build first steps towards augmented reality assisted maintenance. And obviously, we had some problems with that. Oh, I wanted to change the word to challenge, but yeah. And the most important problem here is that most AR researchers don't know the complex processes in the chemical industries. And on the other hand, most technicians in the chemical industry don't know what's possible with augmented reality today. And so our first challenge was to bridge this gap. And I want to present you how we have done this. And our approach was to use the specified human-centered design approach and to have first one iteration of this approach, and I will present now what this looks in practice. So we first had to understand and specify the context of use, then specify the user requirements and produce first design solutions. And then we had to evaluate the designs in the face of a pandemic, which was also a bit challenging. Okay, but let's start with the context of use. So to understand this context a bit better, we worked together with an expert from the chemical industry, in this phase only with one, and try to achieve a simplified process of what a worker has to do when an incident appears in the chemical industry. And we try to simplify this process so far that we as AR researchers can work with it actually, and also work in student projects on this without threatening the students too much. So in our example, we have a worker or a technician in the chemical company. Let's call him Mr. Maintainer. And he gets the signal that there is a sensor. Let's let it be a pressure sensor in our example. And this pressure sensor shows values that are not in the accepted range. For example, there is too low, the pressure is too low. Then our maintainer has to go to the actual plant, which can have the size of a small city, and has to navigate through the right section of this, big plant. And when he finds the right section, he has still to orient himself in the three-dimensional reality here to find the right component, so our sensor in principle. And then, in most cases, the sensor is not the problem, but some functionally related components are the problem. So at the same time, he has to take a big diagram with him, which is a PNID diagram, a piping and instrumentation diagram, where he can see the components connected to each other. And there he also has to find the right sensor and the closely connected components. So for example, a pump or a tank. Then in our use case, we make it a bit more complicated because our maintainer checked the PNID and the components, but did not find the right one. But instead, the problem was a small valve, Deutsch Ventil, that was not depicted in the PNID diagram, which is a common use case. Often these diagrams might be outdated or not on a level of detail that is good enough to show all components. So after this, our maintainer processes and thinks how to solve the problem. In this case, it's very easy. He has to open the valve, so he repairs it, and then he has to communicate with the control room to make sure that the sensor data is now in an acceptable range. And afterwards, in principle, he should document this issue, that the valve is not visible in the PNID, to the engineers so that they can give out an updated version of the PNID plan. I said in principle, if you are a bit pessimistic about how often this documentation really happens, you are right. So this is just a quick overview for AR researchers. So this is not good enough for maintainers to do their daily work, but it's good enough for us to start thinking about how we can enhance this process. And in the first step, we separated the main user tasks. So how to find the right plant section, how to find the right component, and so on. And then we prioritized where we think that we can help most. So, for example, we canceled out the navigation task because this can be done with GPS-based navigation pretty easily. And we also, for now, canceled out the information accessibility, so we don't, for now, include sensor data to our prototype, because here much work has to be done on the side of the chemical industries to build good APIs to start really using the sensor data in our augmented reality applications. But overall, we can say that this process as it is demands high cognitive load from our Mr. Maintainer, and so we can help in some cases. So obviously, next step was to look at whether there is already a solution for our problem for process industries. And actually, we find some related work in the field of component identification. So here you can see that there are pipes already highlighted with their components. We also find some solutions for education and for information access, but no workflow for maintenance and maintenance in the chemical industry specifically. So this is what we want to achieve now. To do so, we first had a software workflow concept, which is that our maintainer first has to accept the mission, and then he can see the component supported version of the component identification in the P&ID diagram, and at the same time in reality. And only if both match in future, we will enhance the scene with additional information, because if they don't match, we might even make it worse. So in this case, we only upgrade the P&ID plan and the virtual model. And then we start building a demonstrator, because now we are familiar with what the use case is as AR researchers, but it is still difficult to communicate to our or to the later users what we want to achieve and whether this is relevant for them. So we built first a prototype for two of the functionalities, and we also had an interactive CAD scene registration. So not an automatic one as we've seen in the talk before, but we done this by hand for our mock-up. Yeah. And then we had two design solutions as well for the component identification in the P&ID plan. You can see this on the right side here, as for the component identification in the real world. So here you can see that we aligned a CAD model with the real world, and then we used this CAD model to highlight the tank in this case, if it is in the camera view, or by showing a flying arrow if it is not. And here you can see two different versions of showing the P&ID plan. And to explain them a bit better, I use the videos instead. Because for the P&ID plans, we had the problem that we have to work with handheld devices. And you might know, the display size is quite limited for these devices, and these plans usually have a format of A0 or A1. So showing all the information on a small screen is not so easily possible. And so we have two hypotheses how this could be done in the future. One version is an AR version. So here the P&ID plan is world anchored. And the other one is a UI version where you have to zoom in by touch and repositioning the P&ID plan. And to make it complete, here you can also see the videos of the highlighting and the arrow-based navigation. So with this small demonstrators, we were now able to get a first feedback from our future users to see whether these features would be relevant for them. And since this study was conducted in the times of the pandemic, and our users were not situated in the same city as we were, we had to conduct or get our feedback online. And we used therefore a video conference and invited 5 specialists from the chemical industry. So this is definitely not representative, but it is a first step for getting feedback. So you might notice that our features so far are not very advanced, so it does not make sense in this early step of research to do a quantitative analysis. Instead, we used the qualitative approach to get a first feedback, and we show the functionalities in the short movies you've seen already. So the feedback was overall very positive, especially for the navigation functionalities. And our target group also told us that the scene complexity is the main reason why this functionality will be very helpful in the future. Since you might have, for example, valves that are under the ceiling, and yeah, it is not such a good situation if you first have to identify where it is and put a letter there and go up and see, okay, it was the wrong valve and you have to reposition the letter. So in this case, if you highlight the correct valve, yeah, this would be very helpful. And also in chemical plants, you have many foreigners. So for example, firefighters or external technicians like from the pump manufacturer. So for these people, our target group said this functionality would be very helpful. I put a little word on top of this slide because already during the feedback round, I was a bit concerned about bias. And it turned out that two of our interview partners are actually working in the same or in a similar project. So our contact from the industries selected for us or interview partners that are very welcoming for our features or that liked our features very much, partially because they are working in a similar field and were already motivated to say that this is a good feature. So just to be careful with this announcement here. And for the other feature, I also asked about the usability of the AR version, and there were concerns about the ergonomics of this version. So how long do a user wants to hold up a smartphone this way, and whether this causes arm fatigue, so to say. So here we have a new requirement. We have to definitely investigate during future quantitative analysis of this use case. And then we also had some or two requests for future features. The one was, especially our technician in the interview said, okay, it would be cool to have a Google Lens-like feature here. So our first hypothesis that our technicians might not have so much idea of what we are talking about was also not so correct. They actually had some ideas, and they said, okay, if I point my camera to the component, then I want to see additional information directly. So more or less this is what we stated already as our feature 5. And the other general feedback was that the combination of seeing the functional data and the spatial data at the same time is also very beneficial, especially for unexperienced workers, so that they don't have to search so long and get more understanding of the two different worlds. Yes. So the main contribution of this early stage of our project was that it presents a realistic use case for industrial augmented reality to the AR community, so that others can also work upon this step and has not to do the same work again. It shows a first prototype and presents a bit of expert feedback. Not enough for getting significant data, but at least to go ahead. And it also collects new emerging research questions. And this was the main reason why I want to give this talk today, because these early stages are not often published. And so it is good to have workshops where we can also publish these early stages. Because as you can see on the next slide, a lot of research questions emerged from these early steps, and many that we could not have anticipated before. So the first one, maybe we could have thought about ergonomics before. But especially this combination of the spatial and functional neighborhood of data is something that is not so familiar to AR researchers. So to give another example where this can happen, think about social relationships. If you are here at the conference, you have relationships to others, and imagine you could visualize these relationships in augmented reality in this room, so you could see who are other peoples that are co-authors of this paper. One is sitting there. What I want to say is it is a new field of research to look in this kind of visualization. And yeah, other topics that are more or only related to industrial augmented reality is that we have to integrate our AR front end now to existing infrastructures. So the chemical plants already have APIs for their sensors that are not standardized now. So this is a task for the engineering side, but we also have to adapt to that this already exists, and that we cannot say, okay, you have to change your world, we have to adapt to them, or we have to find a good interface between both worlds. And then we need a software engineering workflow for augmented reality, which is especially important because augmented reality is much closer to actual physical tasks than other types of software. So it might not be enough just to have UML diagrams, for example. We also have to investigate the scenario around the software we want to use to see how large is the scene, how much changes in the scene while we are using them, and so on. So this is another new topic that evolved, we discovered. And what I definitely have not expected was this topic of large diagrams, to see how we can put such large diagrams in scenes with limited field of view. And this is also important, for example, for the construction industries where you have the construction plans, or for electrical plans. Yeah, and then our partners in the mechanical engineering also have some tasks. For example, we need more information about which information and data is actually really necessary to have at hand in the real plant during the maintenance. So much work to do. And our next steps are now to further specify the business processes and roles. Actually, this is done and will be presented in the near future. And then to bring the use case example to an actual demonstrator, so that we can really show it to the experts with an augmented reality scene. Then we need a workshop with more technicians. So actually the data is also collected already, but it has to be evaluated completely. And this step already shows that the navigation is more controversial than our first target or first interview partners stated. So especially internal technicians are a bit worried about having such navigation assistance, because they fear that future generations of technicians will not learn to orient themselves in the scene. And if the system then crashes, then this would be horrifying, so to say. Yeah, then we have to implement the data access, the missing feature 5, and we want to investigate similar scenarios like remote guidance and the evolution of digital twins, which is basically how to put the missing valve into the planning data or the digital representation of our plant. So here you can see the references, and you can also find them in the paper. And with that, I say thank you for your attention.
Thanks, Linda. And also thank you for highlighting the importance of workshops. We appreciate that. Do you have any questions?
Yeah, thank you also from my side for the presentation. I mean, when it comes to remote support, actually there is a lot of software already available. Have you looked more into detail what available software could help you? I mean, definitely not for all features, but at least for some.
For remote guidance specifically?
Yeah, and also supporting remote maintenance or showing diagrams, PDFs or whatever.
Yeah, starting with remote guidance, obviously there is much software that does this already with video streams, so that you can annotate video streams, like TeamViewer Pilot is maybe the most prominent one, or the Microsoft solution for the HoloLens. We looked a bit into TeamViewer Pilot, and I cancelled out the part with the HoloLens for now, because we have some external requirements that does not allow us to use head-mounted displays, because there are explosion safety standards in the chemical industry that does not hold for actual head-mounted devices. one specific about the remote guidance part is that you often either have an asynchronous one or a task-based one without a person doing this, so you have a checklist, or you have the video-based ones where you have another one on the other side sitting and doing the task, not doing annotating. So we have to investigate which one is more beneficial, especially since not always there is network connection in the plans.
Thank you. Any more questions? There is time for one last question before going to break. Okay, so what are your next steps concerning evaluation or user study? You did this one study now, what's next?
Okay, so one next step is definitely doing an A/B test with the PNID versions here. This is quite obvious that this would be a interesting step to see which one is more usable with respect to SUS scores, for example, and also investigating handheld usability scores for this one to also investigate the arm fatigue, for example. Yeah.
Okay, thank you, makes sense. Thank you very much. We will now go into a 10 minutes break. See you in 10 minutes back here. Thank you.
So, welcome back to all of you. I'm glad no one left. Actually, even more people joined. That's great. So, welcome to this second session of our workshop. Let me just already now introduce Tanja Ziegert from TU Wien, Technical University of Vienna. And she's presenting a paper about Ready for Industrial Use, a user study of spatial augmented reality in industrial assembly. Thank you, Tanja.
Thank you, Thomas, for the introduction. So, today I will present our paper on spatial augmented reality. My name is Tanja Ziegert, and I'm in the research group of human-machine interaction at the TU Wien. So today I will present you first the motivation of our research, then go ahead with our research methodology, then show you the results of our user study, and then conclude with limitations and an outlook. So let's start with the motivation. So with rising complexity in manufacturing and the need of providing information at the workplace, there is gaining importance in assistance systems, especially for worker assistance systems like digital systems or augmented reality systems. And also the use of spatial augmented reality is increasing in manufacturing. So this means the projection of information directly into the field of view of the workers, and about 8% of the AR applications are already implemented with projection systems. And the use of projectors of spatial augmented reality allows hands-free working for the workers, and also to adapt to operators' needs. And it can also improve ergonomics, for example, when reducing unnecessary movements when rotating to look for the information. And the main challenges in there are the projection quality, the accuracy, the interaction, and also the user acceptance. And today I will present you our study comparing worker assistance systems like a tablet, what you see on the left side, which is already quite common to use in manufacturing, and a spatial augmented reality system on the right side, where we have the projection of information directly into the field of view of the worker. And therefore we have a total of 35 skilled workers in a company, and also 43 students who tested different scenarios and filled in a questionnaire afterwards. Therefore, we used a multi-criteria evaluation and did also get some qualitative feedback on there. So we used this multi-criteria evaluation model, which we developed already 2 years ago, and it is to evaluate industrial AR and VR use cases or systems, and therefore we picked 2 dimensions, which is process and user. So we looked on the one side of the process of the company criteria like productivity and quality, and the other side also human-centered criteria like ergonomics, workload, user acceptance, and usability. And on the right side, you see the measuring methods, how we measured each single criteria. For example, for the productivity, we did time measurements and the quality grade. And for the user side, we did for the ergonomics, we used the rapid upper limb assessment, in short, this ruler, and also I got some quantitative feedback on that. And then we had the workload with the NASA RTLX, the user acceptance with TAM, so the technology acceptance model, and the usability with the system usability scale with SUS. And for that, we developed a use case for the user study, which is an industrial control cabinet. So this is equipped and wired, so you can see it here in the middle. And it shows a step-by-step instruction, which is once displayed in the tablet solution and once with the projector. So on the tablet, the information is displayed in more detail, so there's more text and images, and also you can look at videos optionally, and the projector only pictures the most important information like material number or which tool to use and the positioning of the parts to assemble. And also for each new step there is an assembly video to look at, so to get the information you need. And the interaction is for the tablet is with touch, and for the projector it was with a Wi-Fi button to go to the next step. Then the next step is the research methodology. So before the study, the participants read and signed research ethics and privacy forms, and then they filled out the demographic data and got instruction on the task and also on the assistance systems. Then during the study, the participants, of course, did the task, and we as the researchers, we measured the time and the quality grade. And after the study, the participants filled out the questionnaire and did the evaluation of the system. So we had 2 groups of participants. One was the one with the skilled workers, where 35 skilled workers in a company who really working on assembling of electronic control panels took part on the study. And then we had 43 students with no previous knowledge in any kind of assembling of electric control panels. With the demographic data, so we had a quite male-dominated participants. So in industry it was even more with 94%, and in with the students we had 80%, which is quite industry standard in Austria actually, with 20% women in industry, or in production at least. Then from the age, the skilled workers were a bit older, so with 36 years old more or less, and the students with 28 years. And then we also ask about the technology affinity, so how good they feel with using new technology, and those were both quite similar within the groups and also within the technologies. Okay, then let's go to the results, what we found out, how this was. So here you see again the different criteria. So we started with measuring the process time, and the process time is not very surprisingly that the skilled workers were a lot faster than the students. This is the first. Then also we had the quality grade. So there the tablet, for the tablet, the skilled workers performed better than the students with the tablet. And you see for the projector, it was both quite similar, but in total, the quality grade for the students were better when working with the projector, and for the skilled workers, it was the other way around, so it was better with the tablet. Then we also evaluated the ergonomics with ruler. So there was the ruler has a score from 7 to 1, so 7 is the worst and 1 is the best, with 7 to have immediate action and 1 is everything is fine with ergonomics. As the use case was overhead working, it's still quite bad for both, so it's 6 for tablet and 4 for projector, as there is still a lot of improvement potential in the use case itself. And we also wanted to have some overall ergonomics feedback from the participants. So we asked, how did you feel with the organ, or how do you think the overall ergonomics was? And there the projector was better than the tablet, and also in general the students rated the overall ergonomics worse than the skilled workers. For the workload, so we used the NASA TLX or ROTALX, and there the students rated the workload higher than skilled workers, and their workload between the systems within one group are rated very similar. And for the user acceptance, the students show a higher acceptance than the workers, and the acceptance of the tablet was higher than for the projector, and especially the workers had a very low acceptance toward the projector. Then we also did the SUS rating, and therefore we had the tablet, the students rated the tablet was excellent and the workers as good, and the projector also similar to the user acceptance, also students as good and workers as only okay. And then we got a lot of qualitative feedback, and I've summarized it here in a few sentences. So in general, mainly the skilled workers gave feedback on quality feedbacks on their open questions. Students hardly didn't give any feedback on that, so this is also a reason why it's better to ask directly in that skilled workers in companies, not only students. And the feedback we got is, especially in tablet, there was too much text on the tablet and it slowed down the process. And especially for the skilled workers, they are used to work with this kind of assembly. They said that the first picture would have been enough for the whole assembly instead of going step by step through the whole instruction. And for the projector, it was quite clear that so most of them proposed to use it for new activities and for training, and not for serious production, because it also slows it down, and also it's quite inflexible in the adjustment of the information. There were also some limitations on our use case or on our study. So we figured out that the use case for skilled workers was too easy, and for the students it was too hard, so it was kind of hard to compare it then. And the study also took place on 2 different places. So we did the one study with the skilled workers directly in the company, and the other one we did in our pilot factory of the TU Wien. So there were different light conditions which might have also influence on the usability score, for example, in the projector or also the acceptance. We also have maybe some learning effects by watching others and also doing some more scenarios. And the sample size, of course, always could be a bit higher. So let's come to the conclusion, come back to the question from the beginning. Is spatial augmented reality ready for industrial use? So we are mainly looking at the workers now, because this is actually the main question for the industrial use. So the protection system is rated good, but not yet mature enough for series production. And suggestions were made mainly to use this kind of system for training in new products. And it improves ergonomics, that's what we saw in our study, but the usability and user acceptance is still rated low from the skilled workers in industry. So the protection system needs some further improvements to be entirely accepted by the skilled workers. And this brings me to our outlook, where we our next steps are going to. So in further research, it needs to run more stable in industry setting to really be used in serious production, and also the adaptability of the instruction, for example, depending on the qualification of the workers, could be a further step to improve the systems. And also there was also a feedback that it would be good to have an automatic detection for switching to the next step, so you don't always have to switch to the next step by hand. Yes, this was it from my side. Here are the references, and yeah, I'm looking forward to questions if you have any. Thank you.
Thank you, Tanya. Are there any questions from the audience? No? Okay, yes, one.
Thank you. Do you have an idea what are the main factors why the system is not mature enough for mass production right now? Or do you have any ideas?
Yes, so there are some actually. So first of all, the system we work with the dynamic projection system, it's very, to say that, the currency is not super precise yet. So as soon as you're moving something, it's hard to get the right position. This is one thing. Also, the lighting condition was one point. So people were moving like this in front of the cabin, and also the adaptation. So especially in this assembly or in this area of manufacturing, they have lot size 1, and if you want to adapt it to each of those parts, it takes a long time to just adapt it for the assembly or for the instruction. Yeah.
Okay. Any more question? Yeah.
Thanks for the sharing. Since we're talking about the industry adoption, so have you considered about ROI, the return of the investment? So, for example, if the company decide to really adopt, or the industry decide really to adopt such solution, they need to invest to buy your product, right? So, have you considered the ROI, the return for the investment?
So the return of investment, you mean? Yes, we calculated it once, but I think it's not very, how to say that? It doesn't say a lot actually at the moment, because nobody would use it like this at the moment. So still, if it would have a good return on investment, it's still not very usable at the moment. So there would be further improvements be necessary.
So what could be the major challenges? Because at the end of the day, if you want to persuade the industry to adopt such solution, the first questions you always ask is ROI. So how are we able to improve the ROI in future? So make sure it can really be ready for industry adoption.
Do you mean how to improve the ROI? So mainly this is part of the time where you have we saw that before, that it's faster than with the tablet. So by that you can also get faster and have a higher or faster return on investment, and also with the quality. So those two are the main effects on the ROI, actually.
Okay, thank you, Tanya. And let's move on to the final presentation for this afternoon session. I do not have to introduce you to Josef because you already know him, but now he will present his work about analyzing the potential of remote collaboration in industrial mixed and virtual reality environments.
So, thanks for the introduction again. I'll introduce myself again. Josef Wolfertsberger. I'm teaching at the University of Applied Sciences in Upper Austria, and in our research we are doing a lot of work concerning industry and how to use technology to support certain processes in industry. And the work I'm going to present to you today was mainly done by Daniel Niedermeyer, a great researcher and programmer in my group. And he actually came up with the idea of what I'm going to show to you, and he's the main implementer of the whole thing, and that's why he's main author. I have just the honor to present it to you. We have already heard today that maintenance work is extremely important, not just in chemical industry, but also in very much other sectors in industry. And what we have seen within the last 2.5, 3 years during this pandemic is that industry has a huge problem to send workers around the world to do maintenance work, to repair machines. And in general, this raises the question, is it really necessary to send people around the world to repair a certain machine, or aren't there some technological means to support these processes, as we have seen already today in another presentation? And you know, of course, some of these tools, Microsoft Remote Assist, and the first one is an application by Reflect, for example, in Munich, a company. And we also developed an own version of this whole thing. At the same time, these versions appeared on the market. So what it is actually is we are working on 2D video information and document this information with virtual annotations that sometimes appear directly in the field of view of the worker, and this we do this with the goal to support this location-independent work. And we raised the question in our research group, is this everything we can do, or are there different ways to support this location-independent work? And we also asked ourselves, does it make sense to add a third dimension to the whole thing, to this whole idea? And so we came up with this idea here, which is called SPARTA, Spatial Remote Assistance for Distant Collaboration. So the idea stays the same, with the difference that we don't share normal videos between these users. So there's always two sides. A local user who's in need of assistance, and an expert user, maybe in a back office in another side of the world, who provides assistance to help this local person. And with our approach, what we do here is we make a 3D scan of a real environment on the local user side, and we transfer this point cloud to a VR user on the other side of the world, and with a goal to make a shared space for both users. There are right now some limitations in our work. You will see this in a second in a short video clip. What we actually do is we are experimenting with new ways of visualizing data, 3D data, in mixed and augmented reality. So before I show you this short video clip, some remarks on the hardware we use. We use a Microsoft HoloLens 2, so it's not really usable for the chemical industry right now. And on the other side, we use a HTC Vive Pro device for the remote user. But in our implementation, you can use any other VR headset right now. We don't use any specific features of HTC Vive Pro. We wanted to develop a solution that works with off-the-shelf devices without any modifications. We also don't use any additional external sensors. And we did some research, and most of the existing solutions that are comparable to this one use external sensors. We don't use these right now. And there is also no manual calibration required right now. So to get a glimpse of what this application does right now, and it is a prototype, this is me actually standing in our laboratory in a fictional use case where I have a problem with this 3D printer in front of me, and I ask someone to help me repair this 3D printer. And what happens here now is I put on the HoloLens 2, and I see a virtual representation of a remote user standing beside me. This virtual user, or this real user, is somewhere else at the University of Applied Sciences in Upper Austria using a virtual reality headset, HTC Vive Pro in this case. And what we can do right now, the VR user can now activate the depth camera of the HoloLens and in more or less real time he gets a glimpse of what my real environment in the lab looks like by visualizing this point cloud. So as I move my head, this point cloud grows together with the color information for every point, and the VR user, the remote user, gets an impression of where I'm standing and where the problem that I want to deal with is located at. So I move around now with the HoloLens, and this point cloud starts to grow. And right now we come to a situation, also the VR user can walk around, of course, in this point cloud, since it's real 3D information. And now the VR user switches to something that is called live mode. So normally this point cloud is saved as is, and if something would change in the real environment, it wouldn't be updated. And in this live mode here, this point cloud gets updated, like when I open the drawer, as you saw here. So he now guides me to take this plate out of this drawer and put it back to the 3D printer to repair this machine. So this is what happens right now. This is again a view of the point cloud, and here you also see the biggest limitation so far of the system. The depth camera of the point cloud or of HoloLens 2 is not very high, or just much too low to use it now in real industrial settings. So it's not able for the VR user to reveal any details in the environment. So this is a work in progress, as I said, and we cannot artificially raise the resolution of the depth sensor of the HoloLens. So we will stick to this resolution. That's why we integrated this photo function, so the VR user can activate the photo camera of the HoloLens if he or she needs to see any additional details of this scene. That's what actually happened here. And now this VR user guides me where to switch on the 3D printer. Everything works fine as expected. And everything is working fine and everyone is happy in the end. There's also this nice artifact of the hand you see here from the point cloud. You can move around the picture here, watch it, and everything works fine. So this is just a glimpse of what this application can do. It's a work in progress. Some words about the technical implementation, what were the challenges here. So we're actually using two different cameras of HoloLens. The one is the depth camera, and the one is the normal HEB camera, the color camera. And both cameras provide very different kinds of information. They have different field of view, they have a different resolution, they also have different timestamps. So in the first step, what we do in our application is we have to align these pairs, color image and depth image pairs. And as soon as those information is aligned, we transfer it to the other side, to the VR side. And on the VR side, the point cloud is reconstructed again and more or less in real time. So the whole thing works with something like less than 1 second of delay, depending on the network speed. So we capture depth and color image on the HoloLens 2. We visualize this information as a 3D point cloud, not just the depth, but also the color information. We have this live mode and the recording mode you saw in the video, and we show each other, both side local user and remote user, as virtual avatars. We integrated the standard functionalities for hand tracking and head tracking for both sides to make the interaction a bit more natural. We have this laser pointer interaction, maybe you've seen it in the video, to reveal details or to show details in the 3D scene. And we have this sharing of images and photos to reveal further details. We did make a first pilot study of the whole thing. We just wanted to know how people react on this new kind of interaction and visualization in the field of remote support. And we invited for this first user study 24 participants. All of them were students at our campus. We also did this during the pandemics. We had a lockdown light at our university, so we were not able to invite external visitors to university, so the whole thing might be a little bit biased, of course. We asked them to solve a set of tasks in pairs, so always 2 and 2 students together. Here you see an overview from the paper of the task description. So what they had to do is there was one side slipping into the role of an expert user who helps the local user. This was the other side. And the HoloLens user started to scan the environment, which was built up then, this point cloud on the VR side. Then they had to locate a copy machine. They had to print a specific document. They had to take the sheet of paper, put it somewhere on the table, and so on and so forth. Then we had to find a suitcase in this room. And the VR user always guided the HoloLens user through this process. We didn't measure things like time or error rate or some things. That's much too early. Looking at this early prototype, what we wanted to know is simply how do people react upon this prototype, and we measured demographic data, of course, and the perceived workload, NASA TLX, raw TLX in this specific case. So we wanted simply to know, is it exhausting to use the system? Do they like it? Do they not like it? Why do they not like it in case they do not like it? You see here we had local user side, that's the blue one. We see that for them it was mentally not demanding to use the systems, but on the other side, those people who played the role of this expert users using the VR headset, they said that it was mentally really demanding to use it because what they were looking at was a very coarse representation, very rough representation of the real world, looking at this partly very dark, very coarse point cloud, which made it really, really exhausting for them to use the system. So this is definitely something we have to look at. For example, another issue was that HoloLens users, they did not have a direct feedback of which parts of the environment have already been scanned and which not. So they didn't have any feedback how or what the VR user sees right now. This is also a big issue. So in the next step, and after doing bug fixing and things like that, first of all, we want to think of ways to improve the visual quality of this point cloud in some ways, perhaps by presenting it as a mesh, for example, as an optimized mesh instead of a point cloud only. And then we think of use cases to test this application in an industry-like settings where we then could measure things like assembly time, error rate, whatever we want. To conclude this, we are actually right now experimenting with novel approaches in this field, with novel approaches, how to visualize and transfer data from real environments to virtual environments. We are also experiencing or experimenting with new ways of interactions in this setting. One important thing for us is that we use off-the-shelf devices with no specific modifications or external sensors. We, of course, see, and you can also see it on these pictures on the right side, that the resolution of the depth sensor is right now too low to reveal details in a complex scenario. We don't have any way to improve the quality somehow right now. Details are completely lost in the reconstruction. This is the hardware limitation I was just speaking of. And of course, you are looking for ways to make the system more comfortable and intuitive to use for future approaches. So, if you're interested in trying the whole thing out, we are thinking of putting the whole thing on GitHub or somewhere else to make it available for the public with the goal to improve it together maybe, or if you have your own ideas on how to improve the whole thing, just approach me afterwards. I can give you a link later on if you want to try it. Thank you very much.
Thank you, Josef. Yeah, there's a question. Great.
Thank you. Thank you for this wonderful talk. I just wondering, so you mentioned the depth camera, you use the depth camera to capture the point cloud, right?
Right.
So where do you put the camera? Is that on the head or something?
No, it's actually directly integrated into the HoloLens. Let me quickly show it to you. It's
okay.
somewhere here.
Okay. So as you mentioned, the depth camera is pretty low quality.
Yes.
I mean, if you use, for example, other kinds of the sensors, probably the computations will increase, you know.
Definitely, yeah.
Yeah, and the real-time performance cannot be achieved. So do you have any idea to address this? I mean,
No, definitely not. The whole thing works in real time because the depth sensor's resolution is so low right now. So
Yeah.
if the resolution would be increased, of course, then the real time functionality would get lost, maybe.
yeah. So maybe I have a suggestion, but it may not work. I'm not quite sure. Probably because you already know the remote user and also the local user, probably to pre-process this kind of environment in advance, to make sure, I mean, to make it just like a pre-processing step, and so that you can directly import this kind of scenario or environment into your program. So this may
Yeah.
solve this. Yeah.
We thought exactly about this, to pre-record a known environment and just show changes in the environment, for example.
Yeah. So it have to be very detailed. Yeah.
Exactly, yeah.
Yeah. So another question is regarding, because currently you are only having 2 users, right? So is that possible for multiple users? I mean,
Yeah, definitely. We are also developed this in Unity. We also have it integrated, this network feature or multi-user feature already. So right now we only tested it always with 2 users, but it is possible to gather like 10 users also in the same environment.
Yeah. Okay. Thank you.
Thank you.
Sure.
Thank you. One more question.
Hello. So can you just simply replace the depth camera with the 2 RGB cameras? So just like taking VR videos, you take the videos on the left and right RGB camera and just send the RGB videos, so showing to the other user. So as he is wearing a VR headset, he will see the left. So he will see from the left screen and right screen 2 different RGB videos, so he will have a sense of a stereo sense, and then you don't need to transfer point cloud.
Yeah, this would be definitely possible, of course, yeah. We just wanted to experiment with real 3D data, with the real point cloud, and use the depth camera of the HoloLens and to find out more about the possibilities of depth sensors right now. But this would also be a solution, yeah.
Okay, so if there are no more questions, and also since the construction work seems to start next door, probably it's a good point to say once again, thank you, Josef, for your presentation. And for sure also thank you to all of you. Sorry, one question. Josef, on the screen for you.
Can you read it out for me?
Yeah. Would it be possible to use the point clouds to identify common objects using some object detection algorithm and replace the PCD with the CAD models? Or is the generated point cloud data too coarse for further processing?
I would say it's much too coarse to pen smaller objects. We actually thought about exactly this approach, but we haven't tried it out yet.
Okay. Good. Then, once again, thank you. And also thank you for having us here, our workshop. And yeah, have a nice evening and try to get out to the real temperature here. It's probably a bit easier to accommodate. Thank you very much.